Welcome to day one of the 6PPD State of the Science Forum. My name is Tanya Williams, and I'm honored to be your host for this two-day event. We're thrilled to have you here, whether you're joining us from across the country or from around the world. In 2020, researchers in the Pacific Northwest identified 6PPD quinone as the long-sought cause of coho salmon deaths during spawning runs. This compound, formed when the tire additive 6PPD reacts with ozone, is now recognized as one of the most toxic chemicals to aquatic life globally. That discovery set off an international effort to understand and reduce its impact. Much of this breakthrough was made possible by years of dedicated work from scientists including Ed Kolodziej at the University of Washington, Jen McIntyre at Washington State University, and Nat Scholes, formerly of NOAA. Their contributions remain foundational to the research and to tribal nations who depend on healthy salmon populations. Federally recognized tribes in the United States are sovereign, self-determined governments whose reserved and inherent rights are protected under the U.S. Constitution. Salmon and other aquatic species are central to tribal cultural practices, food sovereignty, health, and identity. In 2023, tribal nations petitioned the U.S. Environmental Protection Agency to ban 6-PPD under the Toxic Substances Control Act due to concerns over salmon mortality from 6-PPD quinone. Continued harm to prior at-risk and endangered salmon populations threatens tribal treaty reserved and inherent rights to time immemorial resources, cultural relationships, and traditional food systems. Since the discovery of 6-PPD quinone, the research field has grown rapidly. In 2024, the Interstate Technology and Regulatory Council published the first guidance on 6-PPD, an important early synthesis of what we knew about these chemicals. Researchers, regulators, tribal governments, industry partners, and community organizations are now collaborating to identify sensitive species, trace transport pathways, explore mitigation approaches, and map concentrations across landscapes. New findings emerge almost daily, and the momentum continues to build. This forum was created to bring that community together. Over the next 2 days, we aim to deepen our shared understanding of 6-PPD and 6-PPD quinone, highlight emerging science and policy actions, and strengthen connections across research networks. We seek to facilitate broader discussions to continue the momentum to finding solutions to 6-PPD and 6-PPD quinone. Today, you'll hear from 16 practitioners from around the world who are advancing that work. Their presentations represent just a portion of the remarkable research underway, and we hope what you learn sparks new ideas, partnerships, and paths forward. Please note that the views and findings presented today reflect the work of each speaker and are not affiliated with the Washington State Department of Ecology. We encourage you to reach out to the presenters with questions and for more information. I'd like to extend a special thank you to my colleague Heather Duran for coordinating this event and to the entire Forum Planning Committee for helping shape a meaningful program. Before we get started, let's discuss a few logistics. We'll move through 16 10-minute presentations over the next 3 hours. You can follow along in the forum guide, which contains presenter bios, abstracts, and contact information. The link can be found in the Zoom chat or live stream video description. I'll come on camera at the 9-minute, 30-second mark for each talk as a gentle time cue for the current presenter. We will take a 10-minute break at 2 p.m. If we fall behind, we may adjust slightly to stay on schedule and ensure we wrap up around 3. And again, we thank you for your time and participation and being a part of this conversation and for your commitment to advancing solutions. With that, let's begin. Our first speaker is Nathan Ivy from Washington State University.
Thanks, everyone. My name is Nathan Ivy. I'm a PhD student working with Dr. Jen McIntyre's research lab here at WSU. And my research focuses on field-based salmonid ecotoxicology. Today, I'll talk about a major barrier to salmonids and their recovery, stormwater. Anadromous fish are really rare. Less than 0.5% of all fish species migrate between fresh and saltwater, yet here in the Pacific Northwest, they dominate our rivers. Stream rearing salmonids hatch in streams, grow in the ocean, and return home to spawn. It's one of nature's most extraordinary yet fragile life cycles. Let's see here. Okay, so each salmonid species is tuned to its habitat. But stream rearing species spend more time in fresh water, which means greater exposure to whatever conditions or contaminants are present there. That distinction is key to understanding today's topic. Um, let's see. So salmonids are keystone species, and like the keystone of an arch, they hold our ecosystems together. By transporting marine nutrients into rivers and forests, they sustain entire food webs. And when they vanish, it what it does is it signals ecological dysfunction. Now, over the past decade, Chinook and coho have shrunk by 10 to 15%. That's reducing marine nutrient inputs, lowering egg production, and cutting fishery value because smaller fish means smaller catches, fewer returns, and weaker ecosystems. And salmonids, I apologize for the delay here. Salmonids so they're sentinels, sometimes called indicator species, and the use of canaries in coal mines is one of the earliest forms of biological risk assessment. They were effective because they reacted to carbon monoxide before any human symptoms appeared. And ecological management today borrows that same idea. Um, and sentinel species provide actionable early warnings. So who's really playing that role in our watersheds? Now, coho are the canary in the coal mine, only theirs is the creek bed. And spending over a year in fresh water, often in lowland streams, they're exposed to everything that washes off our roads. So the question is, how are they sounding the alarm? Now, urban runoff mortality syndrome, or ERMS, is a storm triggered syndrome that kills adult coho before they can spawn. Symptoms include surface swimming, gasping, spiraling, all ending in rapid death, and mortality rates regularly reach 60 to 90% in road adjacent streams. So these are the coho that made it home, but never spawned. And every unlaid egg weakens the next generation of fish. So stormwater turns ordinary rain into short, extremely intense exposure events that hit fish faster than they can move or adapt. And every time that we brake, turn, or accelerate in our cars, tire particles are shed onto the road. As discussed, is the world's most overlooked pollutant, and rain mobilizes tire wear particles into streams, turning stormwater into a toxic delivery system. Now, UV and ozone crack rubber. So tires use 6-ppd to block the damage. And the reaction creates 6-ppd quinone, the brownish tire bloom that washes off and kills salmon at parts per trillion levels. Now, the concentrations we're talking about are almost impossible to imagine. One cooked grain of rice dissolved in an Olympic-sized swimming pool, that's all it takes to reach the lethal median. And at that concentration, half the salmon die. But how much of this is really in the environment? Now, across the Pacific Northwest, nearly 18 million vehicles shed 3 to 4 kilos of tire particles every year. That adds up to roughly 70,000 metric tons annually, making it a continuous source of pollution flowing from our roads into rivers. Tires directly connect traffic to the health of aquatic ecosystems. Now, adult coho are very big. You really can't miss them spiraling in a creek. But juveniles are camouflaged and small. They're nearly invisible in flowing water. And if they're dying, we won't see it unless we're looking for it. So to find out what happens where no one's looking, we built a study inside a living creek. Miller Creek was ideal. Spring storms consistently exceed 6-ppd quinone concentrations beyond lethal levels, just as young salmon begin swim up and out migration. So We started simple. Two groups of young coho, one reared in clean well water and the other exposed to live creek water during storms. This setup let us see in real time how stormwater itself affects survival and behavior. So hopefully this video here will play. If I can get it to advance. So this is Miller Creek. It's a pretty typical stream. Oh, let's see here. It's taking just a second here to load. Oh, I apologize. It's a little glitchy here, and it's so essentially this was a video that happened right before one of our storms, and it looks relatively clear and clean and relatively harmless. And then I took another video at the exact same time inside our lab, and each aquarium on the right, fish are directly exposed to water from Miller Creek, which is our flow-through system, which allows us to capture the dynamic stormwater pulses as they occur. This really helps us bridge the static lab test to full field studies. And this storm in particular brought a heavy amount of sediment and an accompanying toxic surge. These are conditions that are mirrored in our raceways, giving us a real-time look at how stormwater overwhelms juvenile salmon. So what happened to the fish during the storm? Here's what we saw. The same syndrome that kills adult coho also kills juveniles. And in our 2024 Miller Creek Spring study, let's see here, hoping that this will show up. There it goes. Naive juveniles exposed to real storms saw approximately 80% mortality at each storm event. All controls survived. In all three stores, 6 ppd quinone concentrations rose quickly to 96, 110, and 73 nanograms per liter, and they remained elevated for hours. Now, here we have a yellow box that marks hopefully here it'll populate. I apologize for this. This yellow box marks a 24-hour window where 6 ppd quinone levels exceeded mortality thresholds. This is where we're seeing a sustained pulse of toxicity, which results in over 80% mortality in Storm 3. So our study demonstrates that dynamic stormwater is acutely lethal across freshwater stages with resolved water chemistry. Adults are dying before they spawn, and juveniles are dying before migration. Now, if 800 out of 1,000 elk died on a highway, it would probably make global news. But when 80% of salmon dies in a single storm, almost no one knows. Submerged mortality is invisible, and what we cannot see, we rarely measure. And that's why the Miller Creek Project matters. It makes those hidden losses visible. And urbanization amplifies every stressor year round. More roads means more tire wear, more pavement means more runoff means more windows for mortality. And in phase 2 of our study, we looked at stormwater's effects across entire early life cycles, from fertilization to juvenile. Last year, from October to April, we ran a chronic creek water study using the same real-time system, capturing every storm. And what we saw in those early stages had some sublethal but very serious impacts. And by examining mortality trends, tissue chemistry, and morphometrics, we're learning how chronic exposure to urban streams impact these early life stages. For example, embryo stage fish showed blood pooling near the retractor lentis. That's the eye's focusing muscle. And this was only seen in chronic exposures. This suggests a vascular permeability and impaired vision, which matters because vision is central to foraging, predator evasion, and migration. Now, at the same ATU, stormwater exposed coho developed slower. Delayed yolk sac absorption means delayed swim up and reduced competitiveness. And here, these are representative fry from our control exposure groups. Notice the tail fin at 148 days past fertilization. They're pointed out here. I'm getting close here to time. And there's a few other things, but essentially what we saw was that there was a large amount of A large difference in the total caudal fin surface area, approximately 30%, which has major downstream impacts. And unfortunately, that's all I have for today's time. If you'd like to know more, please feel free to reach out and I can continue going forward.
Thank you, Nathan. Appreciated. We are going to move on to our next presenter. All right, Amira Casey from the University of Washington. Please feel free to pop on camera and take it away.
Okay. Can everyone see and hear me okay?
Yes, you're great.
Okay, perfect. Hi, my name is Amira Casey. I'm a graduate student at the University of Washington, and I'm going to be talking about how increasing temperatures magnify the uptake of tire contaminant 6-PPDQ in juvenile coho salmon. And so, like Nathan was saying, thanks for that great background, by the way. Pacific salmon are an iconic species in the Pacific Northwest, and they are invaluable culturally, economically, and environmentally. However, we can look to the headlines and see that they are not doing as well as a lot of us would hope. And major contributors to their decline include urbanization and climate change. So we also know that salmon need cold and clean water to survive and thrive. And despite the billions of dollars that have been invested into their recovery, we're not yielding the results that a lot of us would hope for. And as human populations continue to grow and expand across salmon supporting watersheds, land conversion to impervious surfaces like roads and parking lots is increasing polluted runoff. And we just saw this video earlier, but also notably over the past couple of decades, coho salmon returning to spawn have been displaying erratic behavior, gaping at the surface, quickly followed by mortality, which is classified as the urban runoff mortality syndrome. So scientists had their work cut out for them in identifying the cause behind these mortality events, and they eventually narrowed it down to stormwater runoff. And as discussed earlier, even further narrowed it down to tire wear particle 6-PPDQ. And then we also have climate change. So climate change is increasing stream temperatures as well as increasing the severity and frequency of these storm events. So that means potentially more runoff. And temperature is one of the most important environmental variables that impacts salmon physiology. So salmon are poikilotherms, which means that a lot of these physiological processes are determined by the ambient temperature of streams. Temperature also primarily influences the toxicity of chemicals in fish by altering their uptake, metabolism, or elimination. So for juvenile coho, the optimal temperature is about 6 degrees Celsius, while for adults, it's around 16 degrees Celsius. And salmon prefer sort of an intermediate temperature. So a mild temperature increase in a really cold stream may actually improve performance, whereas a further temperature increase in an already warm stream would not be good for our salmon friends. And again, some studies have shown that temperature can influence the toxicity of contaminants and actually increase mortality as well. So here's a map of stream temperatures in 2040 in Puget Sound. And here's a map of anticipated increases in urbanization. So we see some overlap here where we have these highly urbanized areas and these really, really hot streams in coho bearing streams. So again, there's these climate-driven processes of increased storm events, as well as the increase in severity of these storm events and increase in stream temperatures, and then urbanization-driven processes. So an increase in impervious surfaces, as well as vehicle traffic density, which could mean a higher likelihood of 6-PPDQ ending up in aquatic habitats, but also we see a heat island effect. So not only are these impervious surfaces heating up urban areas, but it can also heat up runoff that is coming off the top of those surfaces. So both of these are increasing the frequency and severity of extreme heat events. So it's really important to understand how these two major stressors of global concern are going to impact coho now and in the future. Okay, so now that we have some background, I'm going to get into the study. So we focused on juvenile coho salmon, given their sensitivity to both stressors in question, and also a call for more combined stressor research at this life stage. It had nothing to do with the fact they fit perfectly in 250 milliliter jars. So they were perfect size right around March and April of last year. And then here is a map of stream temperatures in coho-bearing streams in April of 2040. So that's 15 years from now. And we see a range of about 6 to 14 degrees Celsius. But we also know that runoff can increase stream temperatures by about 3 degrees Celsius during storm events. So this led to my decision to use the following temperature treatments in this study, given that they are environmentally relevant, but also a good and somewhat conservative representation of this temperature flux from runoff. And again, temperature primarily influences the toxicity of a chemical by altering its uptake, metabolism, or elimination in fish. So I wanted to look at the first part of that question. How does temperature influence the uptake of 6-ppdq in juvenile coho? To do this, I wanted my fish to mostly survive over the 24 hours, so we used a sublethal dose of 50 nanograms per liter. We exposed them for 24 hours to represent a single storm event, and we also had control fish just in hatchery water. This was also repeated twice using 2 different cohorts. So as far as how I'm measuring the uptake of 6-ppdq, I am measuring the loss of 6-ppdq from water as an indirect measurement of uptake. And that's based on previous studies indicating that the loss of 6-ppdq from water is primarily from the partitioning and uptake into organisms rather than the breakdown from abiotic factors. So I took a 1 milliliter water sample at the following time intervals, and I spiked that immediately with methanol and stored that under refrigeration. So for subsequent analytical chemistry analyses, I used a solid phase extraction technique and then ran every sample on the LCMS to get the final concentration from each fish or jar over the 24 hours. Now, to assess whether or not temperature and or cohort influenced the uptake, I fit 4 autoregressive state space models to each reflecting a different hypothesis about the importance of each factor. So the model briefly goes like this. The measured concentration of 6-ppdq is equal to the true concentration plus some sampling error, and the true concentration of 6-ppdq is equal to the true concentration at a previous time plus uptake plus process noise. So the model hypotheses are as follows. The first model says that uptake rate does not vary. Every single fish uptakes 6-ppdq the same, no matter what temperature they were in, no matter the cohort. Model 2 says that each cohort has its own uptake rate. Cohort 1 has its uptake rate, cohort 2 has its own uptake rate, but the temperature doesn't matter. Model 3 is the opposite. This says that cohort doesn't matter, but temperature does. So 8 degrees Celsius in both cohort 1 and 2 have the same uptake rate, but that's different from the uptake rate of 14 degrees Celsius in both cohort 1 and 2. And then model 4 is kind of a free-for-all. This one has 8 different uptake rates, each for every temperature and a cohort combination. Okay, so we saw the most data support for model 3, which suggests that temperature is the influential variable on uptake rate alone. But we also did see some model support or some data support for a potential cohort effect, which I will touch on later. So here are the results of the study. We have the raw data points with the Mars models trend lines plotted over them. And what I really want to point out is our lighter colors here, those are our lower temperature treatments. Those show a slower uptake than our darker colors or our higher temperature treatments. And more notably, the higher temperature treatments had a 50% faster uptake per 30 minutes compared to our lower temperature treatments. So again, we have our estimated percent decrease in 6-ppdq per 30 minutes. Here's 8 and 10 degrees Celsius. We see about 2 to 2.2% decrease. And then we have over here our 12 and 14 degrees Celsius treatments, which both have a 3.2% uptake per 30 minutes. And so temperature may amplify or mitigate 6-ppdq toxicity depending on coho metabolism. So there's a couple different hypotheses here, where it's possible that at these lower temperatures, there's a lower metabolic and biotransformation rate, which means slower detoxification. So 6-ppdq might persist longer in tissues, or it's also possible that these increased temperatures are having a faster uptake, which means maybe a higher contaminant loading. And coho already have a potentially limited detoxification capacity. So this additive physiological stress near a certain temperature threshold could amplify toxicity through both higher exposure and thermal stress. But the true direction of these hypotheses really depends on metabolism and how that sort of influences toxicity. Okay, and again, we did see some potential impacts of cohort effect or genetics, but we still see that same trend where our lower temperature treatments had a slower uptake compared to our higher temperature treatments. So this is important because both climate change and urbanization are major stressors of concern. So kind of understanding their combined impacts on Pacific salmon is going to be really important for managers. And we're hoping to go back out to Wallace River this winter and do a mortality study, but that depends on if UW's Animal Care and Use Committee will let me this year. I think I can persuade them, but we got to give it another shot. So I just want to acknowledge all of my collaborators. And I would also love to encourage everybody to check out the story map. This is in the presenter bios and abstract form. There's a link to this, but this is geared more towards a general audience. So thank you.
Thanks, Mira. All right, next up is Dylan Ahern of Herrera Environmental Consultants and Chelsea Mitchell with King County. Dylan and Chelsea, are you available to come on camera?
Yep, I'm right here.
Yeah, just let
All
me.
right.
Hi.
Hi, welcome.
Hi.
Go ahead and advance your slides and get started. Thank you.
All right, thanks everybody. So there's a few names up here, but I obviously Chelsea and I are here, but I want to recognize our other collaborators on this work. So let's get started. I have some animations here. Let me click through 1, 2. There we go. So yeah, some of the first studies on treatment of 6-ppdq, if you all remember back in 2015, before we even knew of the chemical, indicated that the bioretention with a typical 60% sand, 40% compost mix was protective. This was a study by McIntyre and others. And so we knew bioretention was a great BMP for reducing toxic runoff. Right about the same time, though, with some studies that were coming out of city of Redmond, they were documenting just how much nutrient export occurred with bioretention. And when you have a liner and an underdrain, that becomes a big deal, that nutrient export. So there was some hesitation about using that mix to treat stormwater, even though we knew it was protective of coho salmon. So when 6-ppdq was actually discovered in 2020 and in 2021 was when that science paper came out, the region really wanted to use bioretention even more, right? But there was still this issue of the export of nutrients. So what occurred was, about a decade long, a little bit less than that, effort by academics in the region and by consultants, by King County, Kitsap County Ecology to develop an alternate media that would still be protective but not export the nutrients. And so what that looked like was this mix here, which is instead of just being sand and compost in one sort of layer, it's a layer cake. And that is the top layer being sand and coconut coir and biochar. So providing some of those organics, but not having compost in it. And then underlaying that, a 12-inch layer of stuff that would particularly target those nutrient exports, the nitrogen and phosphorus. So that's sand and activate alumina and iron aggregate. So this was tested, and then on top of that, like a compost blanket was placed. So that's not shown here, but just a compost mulch on top. So keep the plants happy, but not export that amount of nutrients. And so this is put through a number of tests, plant growth tests, and it was shown to reduce metals and actually reduce nutrients, not export nutrients. But the question became, would it still be protective when it came to 6-ppdq? So initially, there were some lab studies to look at this, conducted by our own Chelsea here, as well as with Curtis Hinman up at Western. And they determined that in the lab setting, at least, indeed, this mix was very effective at reducing 6-ppdq. When this effort was underway, Doug Howey was explicit in that after the media was developed, it would need to be tested in the field. And so that's exactly what happened up in Whatcom County. So a little bit of a lag, but there we go. And so this study, what we're going to present the data from today, is the first full-scale field study, first data you'll ever see of the HPBSM, that's the new bioretention soil media, deployed full-scale in the field. And what the water quality performance was for it, for conventionals as well as 6-ppdq. So what this site was a sort of conventional roadside swale. The county is very interested in reducing nutrients loading to Lake Whatcom. There's a phosphorus TMDL. And so they wanted to retrofit this underperforming facility with the HPBSM and sort of reroute the plumbing a bit to make it work more effectively. So what we did. We sort of redesigned it, put a liner in, and put in that layer cake that we showed in the previous slide of the 18 inches of sand, coir, and biochar underlain by that polishing layer, and in a bunch of cells moving down the slope here, and then deployed all the monitoring equipment. And I'm going to hand it over to Chelsea to go over the results we saw out there.
Thank you, Dylan. Okay, so I'm going to, yes, there is a lag time, sorry, get used to that. Present results from basically two of our research questions for this project. I'm at King County, and we were lucky enough to be able to partner with Whatcom County and Herrera on this project to sort of piggyback on this existing big water quality treatment project to add investigations about 6-ppdq treatment. And so our first question, even though this forum is about 6-ppdq, I want to touch on whether or not this high performance BSM meets Washington State stormwater treatment goals, because what good would excellent 6-ppdq treatment be if we couldn't also meet these goals that we already have that are really critical to our water treatment. And then our second question here is just, does this high performance media perform as well in the field as it does in the lab for 6-ppdq removal? And so I'm going to be showing, let's see, trying to advance to the next slide, some data from for TSS nutrients and actually metals from the Whatcom County parts of this study. Here we go. And 6-ppdq data from the King County parts of this study, all done by sampling through Herrera. So for our TSS and phosphorus goals in Washington, our treatment goals, we have our for TSS, phosphorus, and dissolved copper and zinc. And here I'm showing on the far left TSS data, in the middle total phosphorus data, and on the right orthophosphorus data for 20 storms. And on the left in each plot is the influent, and on the right is the effluent, the water coming out. And so we can see here that we did meet TSS treatment goals because effluent concentrations were below 20 milligrams per liter. We also met total phosphorus treatment goals. But note that the phosphorus coming into the system was actually pretty low. So this is kind of even more impressive to achieve such high reduction rates. And then orthophosphorus, we did not see any export of this orthophosphorus, even though, the influent concentrations are really low. Seeing no export is kind of a pretty big deal for a system that contains organic materials. And now next I'm going to show you some dissolved metals data. Anytime now. Interesting. Okay, so our treatment goals for dissolved metals in Washington are 60% removal for dissolved zinc and 30% removal for dissolved copper. And just right off the bat, I want to note that the copper concentrations coming to the system are really, really low. But this bioretention facility achieved the state's goal for zinc, but not for copper. And let's see, that is potentially in part because we had such low copper influence concentrations, but we can't really say. And so we've answered that first question so far over across 20 storms, really quite a lot of testing. We've seen that we can meet these treatment goals set up by the TAPE protocol in Washington. But here's the data that I suspect you all are most interested in. This is our 6 ppdq data for the system, which I think is really exciting. So we saw influent concentrations coming into the system between 11 and 72 nanograms per liter. And that's, these samples are collected as flow-weighted composites over the course of a storm. And so these concentrations are sort of representing like an event mean concentration. And so even in that context, we're still seeing concentrations that, reach toxic levels to coho. We're talking about water coming out of a treatment system, not in receiving waters, but still, this is kind of interesting because this area is not highly developed. It does not look like the places we typically see people collecting runoff from. And so that's something to note. And we did not detect any 6 ppdq in the effluent of the system throughout all of these 8 storms. And we're going to continue to do some more testing this fall, but so far, we're super excited and think this media is really effective for treating 6 ppdq. And I just want to, sorry for my pausing with all the lags, but I just want to thank, there's a ton of people involved in this, and someone that I don't have on this list is Chelsea Morris from Ecology, who is the SAM project manager for our 6 ppdq project. All the folks at King County and Whatcom County for letting us partner as well, and at Herrera for doing all the work, field work and stuff. Thank you.
Chelsea, Dylan, thank you so much. We appreciate you sharing your work. And we are going to move on. Not quite sure. There we go. Tanya Brown with Simon Fraser University. Please feel free to come on camera and take control of your slides.
Okay, thanks, Tanya. Or Tanya, we have the same name. Do I just click here and then it goes to the next slide?
That's correct. Just use those little carrots that say Control Heather Duran slides.
Okay. Okay, perfect. Okay, well, thanks everyone. I will try to be quick here, but I just wanted to highlight kind of monitoring studies that we have been carrying out here in British Columbia. And I want to acknowledge my co-authors, which have played a significant role in this work. And also many partners and funders and collaborators that have been involved in this work to date, supporting all the collections. So our work is looking at trying to characterize 6 ppdq concentrations before, during, and after wet weather events in salmon-bearing streams across southwest British Columbia. And then in addition to that, we've been trying to assess the relationship between 6 ppdq concentrations as well as other road runoff contaminants and a number of land use characteristics as well as water quality parameters, and then I mentioned the other road runoff contaminants that I'll go through in later slides. Okay, for this work, I've been looking at characterizing concentrations in over 98, nearly 100 sites. I think we've exceeded 100 sites now. And we're up to about nearly 2,000 samples have been analyzed for 6 ppd quinone. This work's taken place between 2021 and 2025. We generally wait for 48-hour dry period between any of our collection period times for a particular event, and usually looking for an anticipated rain event that's about 5 millimeters, at least 5 millimeters of rainfall. And for some of our sites, or a majority of our, a subset of our sites, we have up to 20 rain events per site. So in addition to collecting water samples for 6 ppd quinone, we've looked at the parent compound, diphenylamine, which is also an industrialized chemical, but also associated with road runoff, and then as well as metals, and then measured YSI parameters, as well as measuring flow every time we go into the field. So these are some of the concentrations where you have 6-ppdq concentrations on the y-axis at a number of our locations or sites in North Vancouver. And so you're looking at before, during, and after. So during is the concentrations in the highest concentrations in the bright blue there, and what you can see here is that we're exceeding sort of these lethal concentrations for coho salmon for both LC50s that are published in the literature, as well as obviously exceeding water quality guidelines that are out there as well. So we've done sort of more of a deeper dive into characterizing the first 41 sites of the 100 or so sites that we've been monitoring. And if we look at those on average, we're seeing about 78% of those sites have concentrations that are exceeding these threshold values in our salmon bearing streams. And then at each of our sites, we've looked at extracting the primary watersheds and then characterizing the land use classification for those watersheds. And then what we can do with that information is start relating the 6-ppdq concentrations with, say, for example, percent road cover, as you can see in the left-hand figure there, with 6-ppdq on the y-axis and percent road cover on the x-axis. We've also saw positive associations with residential cover and commercial cover. And then for some of our YSI parameters, looking at dissolved oxygen or turbidity. And then within sites, rather than across all sites, we've also seen variation between just in terms of relationships with flow, as well as the number of dry days leading up to a rain event. So we can dive into the stats a little bit more, where how do we start to characterize sort of these concentrations across all these sites. So we've used multivariate statistics to start to group our sites with both the 6-ppdq concentrations and the land use parameters that we have for our different primary watershed areas. And what we've been able to do is develop these four different clusters: highly urbanized, moderately urbanized, semi-urban, and relatively underdeveloped. And then we've averaged those concentrations. So each site is going to fit within these different categories. And then we've looked at sort of what are the average 6-ppdq concentrations before, during, and after the rain event that we're seeing. So we are seeing a 7 to 20-fold increase in 6-ppdq concentrations before to during a rain event. And we are seeing that our average concentrations in our highly and moderately urbanized sites, as well as semi-urban, are exceeding screening values. So our next step is to start to kind of feed all this data into adapted model that was used in Feist et al. In 2017. So we've adapted this model, it's a Bayesian model, to use it so that we can do kind of a predictive risk-based analysis map for 6-ppdq concentrations, as well as coho, and relate that to risks that may pose to other salmonids as well, so that we can project other streams in areas that we haven't been able to reach from a monitoring perspective, and try to look at what we predict based on all these different variables as to what the concentrations or degree of risk may be at these particular sites. So what we're feeding into these model input variables are looking at 6-ppdq concentrations, traffic density, percent of imperviousness, etc., land cover, of course, catchment area, as well as our weather data variables are all feeding into this model as well. You can relate, you can look at deriving a latent factor, which summarizes sort of the key patterns into a single variable that we can then use for the modeling. And so what this is showing you is just a projected heat map for the relationship between land use classifications and our latent factor. So we're seeing that road areas, of course, having the strongest effect on increasing 6-ppdq concentrations. So this is just giving you one example of how we're assessing and utilizing the model. And where we're going from here is generating two outputs for this predictive hotspot map. This is where we've extracted much higher density data. Tim Rogers has been working hard on this aspect of the work with myself and others. And then we have other sites where we have lower density data. So we have to sort of take that into consideration when we're doing our predictive mapping, our end predictive maps. And then I'm kind of rolling into some of our results on the occurrence of other road runoff associated contaminants. So we looked at characterizing sort of before, during, and after, and what other contaminants we're seeing that are co-occurring with 6-PPD quinone. And this is showing sort of the contaminants on the left-hand side that are most likely to co-occur, what we're finding in our during samples during rain events. So we're seeing kind of and this is consistent for both our total and our dissolved metals. And so if we were to plot just, for example, zinc and copper, and this is the same if we were to plot the other two metals that were teased out there, we're seeing that a strong correlation with the tire chemical. As well, we're seeing exceedance above on average for water quality guidelines for both zinc and copper during rain events. And then diphenylamine, another widely used industrial chemical that I mentioned earlier. There is some information there. It is toxic to rainbow trout, but the information that is available from a toxicity perspective is somewhat limited. But we are seeing a statistically significant relationship as well with diphenylamine and 6-PPDQ. So in summary, our data have been supporting sort of regular deliberations under Canada's Environment Protections Act, where 6-PPDQ are under re-review. 78% of our sites monitored did have concentrations that exceed threshold values during wet weather events. Our land cover variables are strongly related to 6-PPD quinone, and I've gone over sort of the significant ones that we looked at and what's weighing into our overall modeling exercise. Copper, zinc, cadmium, antimony, and diphenylamine are strongly correlating with 6-PPDQ concentrations in all our during rain event samples. And then we have our predictive hotspot mapping that is well underway. And with that, I will just say thank you. And thanks everyone for being here.
Thank you, Tanya. We appreciate it. Next up, we have Hannah Bion from the University of Toronto.
Yeah, thank you. Hi,
Hi,
everyone.
Hannah. Welcome.
Yeah. Hi, everyone. My name is Hannah. I am a graduate student under Professor Hui Peng at the University of Toronto, and I will be presenting to you today on the regioselective toxicity of aromatic hydroxylated metabolites of 6-PPD quinone. So just for brief introduction, 6-PPDQ can undergo phase 1 metabolism to form two hydroxylated metabolites, as shown here. So one on the alkyl chain and one on the aryl ring. And in our group's previous work, we confirmed that the alkyl metabolite is in fact non-toxic. And so this alkyl hydroxylation pathway serves as a detoxification mechanism, but the effects of aryl hydroxylation currently remain unknown. And so the goal of this project was to identify whether or not aryl hydroxylation increases the toxicity or whether or not that detoxifies similarly to the alkyl pathway. And this work was done in collaboration with Pranav, a senior fellow PhD student in our lab. So there's 3 different possible isomers for the aryl metabolite, as shown. The structures are shown there on the right. And so we first went on to confirm which of these isomers are the major aryl metabolite in rainbow trout, and we were able to confirm with 3 of our synthesized isomers that the para isomer is in fact the predominant aryl hydroxylated metabolite in rainbow trout, which agrees with the previous findings from the Brinkman group early this year. So then we went on to confirm its toxicity relative to 6-PPDQ. And what was very interesting is that this metabolite has comparable toxicity to 6-ppd-quinone. And for anyone that is unfamiliar with how the cytotoxicity experiments are done, this was done using an in vitro toxicity assay using a salmon cell line, which was kindly shared by Dr. Jan Hansen from the U.S. Geological Survey. And as shown here, the para-isomer, because it is comparably toxic, it is likely that it is a major contributor to the in vivo toxicity burden that we observe in fish. But what is very interesting is that this isomer is actually not present in the cell line due to a lack of responsible enzymes. So the toxicity that we observe for 6-ppd-quinone here is not because of the metabolite, but because of its intrinsic toxicity. And so it is likely not essential. This para-isomer is likely not essential for in vitro toxicity in this case. And so then we went on to identify the toxicity of the other isomers. And what was even more interesting is that the toxicity of each of the isomers are different. So the toxicity of the aryl isomers are regioselective in nature. So the structures are shown again here. So in comparison to 6-ppd-quinone, the meta isomer shows reduced toxicity, whereas for the ortho isomer, we observe no toxicity up to 100 micrograms per liter, which is actually quite a high concentration. And so this was very interesting. And kind of highlights that the mechanism of toxicity is likely a very specific target in the sensitive fish species like Coho salmon. And so to kind of understand what might be causing this regioselective toxicity, Pranav synthesized two methoxy analogs of the ortho and para compound, and we observed that this toxicity trend that we see for the hydroxylated metabolites, we see the same trend with these methoxy analogs. And so the regioselective toxicity that we observe is likely not caused by that addition of the OH group, but is rather caused by something else. And so this kind of led us to perform further DFT calculations to understand maybe from an energetic perspective for why we observe such strong regioselective toxicity. And we observed that while these results are preliminary and not perfect, what was very interesting is that, as you can see here in this graph, the ortho isomer, which we saw had very significantly reduced toxicity, has a higher torsional energy barrier to rotation of about 7 kilocals per mole. And 7 kilocals per mole doesn't seem like a big difference, but if you think about it in terms of protein binding affinity, that actually corresponds to a 1,000-fold difference. And so this higher torsional energy barrier might perhaps restrict the ortho isomer from rotating to maybe achieving a more favorable conformation for binding to a potential protein target. Obviously, because we don't know anything about this protein target, this is mostly just speculation, but these early findings suggest that this might be a potential explanation for the reduced toxicity and further highlights the specificity and how selective this mechanism of toxicity really is. And so to conclude, the para-isomer is likely a major contributor to the in vivo toxicity burden of 6-ppd-quinone, but it is not essential for toxicity. And as shown here with the various structures, the toxicity of the hydroxylated isomers are regioselective, which may be explained by the rotational restrictions to achieving a perhaps more favorable conformation for binding. But again, all of this is preliminary, and future in vivo work would be needed to validate the results that were presented today. And just on a final note, I just wanted to highlight that so all of these different products, compounds shown here on this slide, all of them are, the same the same addition of the OH group. It's just that the position of where that OH group is added is different, but that causes very different, that leads to very different toxic effects in the same species. So just kind of further highlighting that this mode of action, although we don't know much about it yet, is likely a very specific target, that a protein target that can only be found within these sensitive species. And on that note, I would like to acknowledge our funding sources, and thank you again to Dr. John D. Hansen and Justin B. Greer from the U.S. Geological Survey for providing the Coho salmon cell line, and Professor Hui Peng and all members of the Penn Group for their feedback and support for this project.
Thank you, Hannah. And next up, we have Mason King with Simon Fraser University.
Hi, thanks so much for that introduction. My name is Mason King, and I'm a postdoc at SFU. I work in Dr. Tanya Brown's lab, who we just heard from 2 presentations ago, and I'll be presenting today on time series 6 ppdq concentrations in urban salmon streams. So our work, we're environmental toxicologists at SFU, so we're focused on these 2 research questions: how high do concentrations get in urban salmon streams, and for how long, so that exposure science. But we're also concerned with how well the fish are doing in those urban salmon streams, so that affects science. However, for today's talk, we'll be looking at those time series of 6 ppdq to get at that first research question, which our lab is focused on. So this stream monitoring is focused on 5 different urban salmon streams, so the catchments shown here in the greater Vancouver area. And we'll talk primarily today about the Wag Creek watershed, which I think is a good example, very typical for these stream systems that we study. And so to look at the map of the watershed, I think it really drives home how highly urbanized this catchment is. We tend to sample with portable autosamplers as far downstream in the catchment that we can go to make inferences about what's going on upstream. And you can really see just how urbanized it is, with red being buildings, gray paved surfaces. So a lot of impervious surface from which rain can run off into this main stem stream. And indeed, this major highway, so Transnational Highway 1, bisects that study site. So what does it look like on the ground? Advancing here. Slow lightning talk, it's all good. This is what it looks like on the ground. So somewhat naturalized stream, and you get at intervals these pipes going into the stream. And so those are discharging from the storm sewer system directly into the stream. So what we're looking at now is base flow conditions during dry weather, but during wet weather, those pipes really get going, and you get this transition from being primarily groundwater fed to being pretty much urban runoff is what is constituting the flow in this stream system. So like I said, we monitor here, there's a gauge in that culvert pictured, and so that helps us to know the flow. What you see here is monitoring from Canadian Thanksgiving 2024, so October. Top panel is a rain gauge in the catchment that gives us hourly range. From the culvert that I pointed out, that's telling us stream flow, so discharge in cubic meters per second. That's going to be the blue line. And then we're taking 6 ppdq water samples at intervals. And so you can see dry weather base flow, we get low 6 ppdq concentrations, and then we get a big downpour of rain and a rapid spike in 6 ppdq from sources like those pipes. and that's quickly diluted in the stream in this example. With the subsidence or the cessation of rain, you get a drop in concentrations again, but subsequent pulses of rain, additional rain later can mobilize additional 6 ppdq from those roads again. And I'll point out here, the monitoring period consists of some baseline samples and then for 1 to 3 days from the start of wet weather. So that's a typical example. Might have to click again. All right, so how can we start to make generalizations about this data when we can see each rain event is very unique when it comes to the amount of rain and the timing of when that falls? How can we generalize this? Well, we can take, say, the example we looked at from October, another one from May, and what we can do is we can start to line those up based on hydrometric variables. So if we do line them up according to the initiation of sustained rainfall, that can help us to get and understand kind of contrasting base flow versus the start of wet weather and storm flow in Wag Creek. But recall, we've actually got 5 different streams in this study system with replicate rain events monitored at each one. So quite a bit of data. And if we look at it all together, I think it starts to show a very consistent story with the dynamics of this flushing. So here you can see the 13 monitoring periods to date. We just finished up 2 more monitoring periods this fall. I don't think it's going to change the story very much from what's plotted here, but basically each one of those lines was the water sample over time. And so you can see a remarkably consistent trend of low concentrations during baseline, and then you get a big spike that tends to dominate in the first wet weather period, and then it tends to be lower. So the box plots that you see here would be, I've taken each of those events monitored, so each of those lines, and calculated a time averaged concentration. And then so we can see the summary of those across the 13 events with the box plots. And what you see visually bears out when we run the statistics with repeated measures, low base flow concentrations, the bulk of 6 ppdq during the first 24 hours of wet weather, with lower concentrations over the second and third 24-hour periods. However, I would point out the important exceptions here, where you get these latter peaks. That tends to be maybe larger amounts of rain falling later on that can mobilize additional material. And so that's how you get some of the high outliers that are seen in the box plots, and that could be potentially important for kind of repeated high-level pulses of 6 ppdq. So I think monitoring with this type of time series data can be really useful. We're going to pivot from the Wag Creek example and consider another focal stream that we monitor called the Serpentine River. This is one that we've published previously. But the point being that we can get this time series data. This is only for 24-hour periods, but we can look at these time average concentrations and just get a good sense of, for monitoring replicate periods within each of those streams, what's going on overall. So in addition to time averaged concentrations, we get, and we also have that flow data. So we can calculate loading, and that can help us to see how effective mitigation is moving forward. Thirdly, we can draw a line on one of those time series where there's a threshold of concern. Maybe it's an environmental quality guideline, maybe it's an acute toxicity threshold value, such as LC50, so median lethal concentration value. That's what I've shown here. So 41 nanograms per liter for a sensitive species and sensitive life stage. And I think what you can see with each of these metrics is that dry weather baseline tends to be lower than the wet weather monitoring period. So for concentration basis, load basis, and then threshold exceedances. With duration, so number of hours above your number of hours that you're above that line of concern, we could say, or we could see anywhere from a couple of hours for a given rain event to the better part of the 24-hour period where those fish are exposed to hazardous concentrations. So takeaways from this talk are monitoring in urban salmon streams. Firstly would be that hydrology is really important to the transport of this contaminant and the concentrations we get. And if you work on this type of monitoring work in salmon streams, yeah, maybe you don't have a fancy auto sampler to automate the water sampling, but that hydrometric data can go a long way towards interpreting, say, whatever you can get, such as grab samples. So we've done stuff even as simple as just like a ruler with a fixed datum, so what you could think of as a staff gauge. I also think very affordable alternatives like depth loggers are pretty cheap and widely available. And so what I found in this data set so far are that time averaged concentrations and exceedance durations are really useful. We can compare them with acute toxicity test data to evaluate hazard. And so what we've seen, for instance, so far is that time averaged concentration for the first 24 hours, we've seen 33 nanograms per liter in these highly urbanized salmon streams. And then we have seen that there are multi-hour periods where you can get above thresholds of toxicological concern. Okay, next slide. All right, so big thanks to a long list of people and funders to make this work possible. Some of that preliminary data from Serpentine River is published at that link, and I look forward to hearing from you all with questions if you care to follow up by email. Thank you.
Great. Thank you, Mason. And next up, we have Timmery Hamill from the California Urban Streams Alliance, the Stream Team, and Laura Baker, Friends of the Guala River.
Okay, can you hear me okay?
Hi, Laura. I can. Feel free to say next slide and I'll advance for you.
Okay, so next slide. So first, thanks to our team, Timmery Hamill, our partner from the Stream Team, Dylan Freebairn-Smith, who's the conservation analyst for Friends of Wallala River. That's our grassroots community group, and our volunteer, Beth Rowland. So the photos that show the Wallala estuary in two different phases. The upper photo shows the lagoon phase with the mouth of the river closed by the large sandbar. The lagoon phase usually begins in late spring or early summer with the end of the rains and decrease in freshwater flows. The lower photo shows the estuarine phase when the mouth is open and the river is subject to tidal flow. The hydrodynamics of the estuary are complex, and the runs of our salmonids are adapted to these complex cycles, with spawners returning from the ocean and smolts ready to begin their ocean phase when the mouth opens. In the upper photo, you can see Highway 1 coming in from the right, which passes through the town of Wallala and is the only thoroughfare. The town of Wallala is a major service site in this rural area where we have gas stations, grocery stores, and some other commercial businesses. The town is situated on a narrow marine terrace perched directly above the river, and behind it is the Pacific Slope, which is heavily forested. All the stormwater from the north end of town to the bridge at the south empties directly into the estuary lagoon. Next slide, please. In 2023, when we first learned about 6-ppdq, we began to investigate the Wallala stormwater system. Our endangered coho population has been nearly extirpated in our watershed, and we've been working on water quality issues to aid in its recovery. We regard the coho like the canary in the coal mine for our watershed, as a previous speaker had mentioned. We also thought that there might be opportunity to work with Caltrans, which is our state transportation agency, to improve stormwater mitigation, because it has been in the process of developing a streetscape plan for downtown Wallala that would involve some stormwater treatment. Once we identified all the pipes, drains, and outfalls of the stormwater system, we hired an eco-hydrologist, Greg Kamen, to produce a technical document to estimate the possible range of natural flows in each of the 3 sub-watersheds in town and to propose possible mitigation for the stormwater. Next slide, please. While most of the research that we've encountered described the impacts of 6-ppdq on coho as an urban phenomenon, we wondered whether the heavy concentrated traffic in Wallala might be a larger source of 6-ppdq than assumed. In 2012, Caltrans estimated the average annual daily traffic in Wallala as approximately 3,000 vehicles per day, depending upon the month. However, these figures are misleading in terms of estimating the actual number of tires that pass through our town on a daily basis. We have many large trucks, trailers, and other large vehicles that use Highway 1 because there is no alternative route. Just one 18-wheeler is comparable in terms of number of tires as 4.5 cars with super large tires. So we believe that the number of vehicles isn't a precise enough metric to use to determine the traffic that poses a risk from 6-ppdq, nor should we assume that rural areas don't have sufficiently heavy traffic to produce significant concentrations of the toxin. And now Timmerie will take over. Next slide, please.
Let's see, we did some preliminary testing of stormwater runoff during rain events following the state of Washington sampling protocols to determine concentrations of zinc, oil and grease, turbidity, and conductivity. Once the EPA testing method for 6-ppdq was approved for lab analysis, we began to collect samples from 2 different sites. We also updated the Stream Team's monitoring plan and quality assurance project plan to guide our sampling methods. And we uploaded our data to the California Data Exchange Network. This image shows our initial testing sites marked with yellow pins. The red dot identifies the main outfall for the central watershed, which collects stormwater from Highway 1, 2 gas stations, and roughly half of a large parking lot. Next slide, please. This bar graph shows 3 groups of sampling periods across 3 sites. The left axis displays 6-ppdq concentrations in nanograms per liter, and each color represents a different sampling event. As shown, concentrations vary significantly among the 3 sites. The red dotted line indicates the action level, LC50 of 45 nanograms per liter for juvenile coho, and the black dotted line indicates the action level, LC50 of 90 nanograms per liter for adults. The middle sampling location is where stormwater from the central subwatershed is concentrated, as noted above. This outfall consistently shows the highest 6-ppd concentrations. Next slide, please.
Every drop of, oh, sorry, I'm
No
back
worries.
again. Can you hear me okay?
Yes.
Good. Every drop of stormwater from Wallala is untreated, concentrated in pipes, and shot into the estuary lagoon. The early storms in October usually occur when the mouth is closed and not subject to tidal flushing, but stormwater is flowing into the lagoon. This set of conditions represents a potential exposure of salmonids in the lagoon to 6-ppdq. The Caltrans Streetscape project will treat some stormwater as shown in the photo. There are blue dashed lines where vegetation will be placed along the street and a green ellipse that shows the location of a bioswale planned for the project. However, the stormwater that poses the largest threat, which is the central subwatershed, will not be adequately treated. Next slide, please, Timmerie.
Okay. There are feasible solutions that can be employed because Wallala's stormwater system was designed primarily for flood control. It conveys large volumes of untreated runoff directly to the estuary. Installing green infrastructure, both upslope and within the Highway 1 corridor, would help capture, slow, and treat stormwater, addressing flood concerns while reducing pollutant loads. We believe that as Caltrans sets priorities for areas at high risk from 6-ppd, estuaries should be at the top of the list, especially those that support coho salmon. Bar-built estuaries that close seasonally should also be considered high priority, as should communities like Wallala, where the town sits directly above the estuary and lagoon. Mitigation for 6-ppdq should be integrated into every transportation project that crosses a salmon stream. Monitoring for 6-ppdq should be incorporated into the North Coast Basin Plan, and the Water Board should encourage collaborations with community watershed groups to support this effort. The state of Washington has launched a public campaign outlining simple steps people can take to reduce their own impacts, contributing 6 ppdq, for example, keeping tires properly inflated. We've adapted some of their ideas and added our own to create an article for the local community on our website, walala.org.
That's wallalariver.org.
wallalariver.org. Next slide, please.
That's it. Thank you.
Oh, that's it. Thank you. Those are fish coming out of the estuary of the Garcia River to the ocean.
Excellent. Thank you to Marie and Laura. We appreciate it. And next up, we have Rhea Smith with the Washington State Department of Ecology.
Hello. Yeah, thanks for the intro. I'm the 6PD Quinone Environmental Monitoring Lead at Washington Department of Ecology. Ecology is working with partners to characterize 6-BPD quinone in the environment to understand environmentally relevant concentrations and hotspots, and to integrate 6-BPD quinone hotspots with ongoing salmon recovery and stormwater management planning to help prioritize toxics reduction solutions in urban areas. So how does it fit into some of the existing issues? Next. So there's a lot of variability in species sensitivity and tolerance to 6-PPD quinone. Many salmonids reside throughout Washington state over a range of these sensitivity and tolerances, including the most sensitive species, coho salmon, that prefer small stream habitats in lowland areas that are more vulnerable to urban runoff impacts. Coho salmon have been considered a sentinel for urban runoff among ecotoxicologists over the last few decades due to the reoccurring coho salmon pre-spawn mortality events that was first documented in the 1990s. Since the identification of 6-PPD quinone by UW-Tacoma and many others, the contaminant has become an important metric and source tracking tool for urban runoff. A local, state, and federal agency and tribal collaboration was formed around the efforts to understand where and when coho salmon are impacted by 6-PPD quinone. Next. So why is there a need to prioritize and identify hotspots? Unfortunately, there's limited resources to retrofit existing stormwater conveyance systems that were built before current stormwater management recommendations. And it takes time that coho may not have in urban streams. Why do we need to strategize about how, where, and when we sample for 6-buquinone? There's limited lab capacity for 6-buquinone analysis at this time, and the goal is to identify hotspots to help focus actions while solutions are being tested and implemented as well. Stormwater event sampling is challenging and takes more specialized equipment and training and/or a lot of boots in the field. Passive samplers is one tool that we've been using that helps standardize methods and avoid storm chasing when you're first doing the screening for the contaminant in the environment. More intensive storm event sampling is focused on hotspots identified by passive samplers or directly observed by pre-spawn mortality events. Next slide. So we conducted some mapping exercises pretty early on that use watershed characteristics like impervious surface as an example, and salmonid distribution GIS layers to visualize where 6-PPD quinone is most likely to impact sensitive species, especially coho salmon. In 2023, we published a story map with an interactive web map to help with site selection for spatial sampling efforts. And there's a QR code there if anybody's interested in checking it out, or just let us know if you want a link to the story map. Next. So a network of research partners help cover more ground and utilize local knowledge to find the optimal deployment locations. Sampling locations have been carefully chosen across an urban gradient previous stream reconnaissance surveys showed the strongest correlation between 6-ppd quinone and impervious surface and used a metric for urban gradient. We deploy passive samplers in mid-October and retrieve them in early December so that they capture several storm events and provide a time-weighted average. We've used both polar organic integrated samplers, which are the ones at the top there. They're also called POSIS, and diffusive layers in thin films, which are DGTs, have successfully collected 6-ppd quinone. Passive samplers have many advantages for initial assessments and source tracking. Next. So the passive samplers provide a time averaged mass loading per stream. We are able to also convert these to concentrations, but for our watershed comparison work, we don't really need to. Using the data from pre-spawn mortality surveys and conducted over the years, we can compare the streams with reoccurring pre-spawn mortality with streams where impacts haven't been as obvious. 78 streams were sampled. 21 of these streams had reoccurring pre-spawn mortality observed, and the remaining 57 streams did not. But I should mention that I think this is mentioned a couple times now, especially in Nathan's talk earlier. It's important to mention that this doesn't include potential sublethal impacts, and recently there have been several ERMS observations of juvenile coho that are harder to detect. So there may still be mortality and sublethal impacts in some of those lower 6-ppd quinone levels that just haven't been observed yet. Next slide. So in addition to doing those geospatial surveys to understand the distribution of 6-ppd quinone across an urban gradient, we've also been doing quite a bit of the sampling that I think a couple other folks mentioned with auto samplers. And these are really to understand the maximum concentrations and the exposure timing of the contaminant. And so we had 4 stations, and they're all located in one watershed. And you can see that it varies just within one stream. But these upper 2 stations, 3 and 4, are in a nicely riparian area, and these ones down below are in a more urbanized area. But we found 6-ppd quinone in all of them, although there's higher concentrations and seems to be more mass in the urban areas. The telemetry stations with the auto samplers are an effective tool for capturing those peak 6-ppd quinone concentrations and understanding how long they persist in the stream. And the telemetry stations upload data to a website dashboard to help visualize and download data and allow us to trigger the start of the sampling remotely, which is nice. In this case, the auto sampler takes water samples every 2 hours for 24 hours during storm events. Station 1 and 2, again, were the higher, and station 3 and 4 were the ones with riparian buffers. But even if you have riparian buffers, there's still pipes that can go straight to the creek and discharge 6-ppd quinone from pipes. And we also collect YSI and velocity information and rain buckets for precipitation so that we can correlate some of the storm event information with the 6-ppd quinone concentrations. This particular urban stream did not ever really run out of 6-ppd quinone throughout the year, so it didn't seem to be mass limited, but rather storm limited. Next slide. EPA, USGS, and King County researchers have been conducting similar auto sampling around the Seattle area to understand the fate and transport of 6-ppd quinone. It's helpful for multiple partners and to study multiple streams to see if we're all seeing similar things at this stage. Next slide. The EPA-led project on Longfellow Creek and other streams mapped here are where pre-spawn mortality, salmon mortality is regularly observed to address two main questions. How do watershed characteristics influence 6-ppd quinone water column concentrations in response to a rain event? And what was the role of the particulates and organic carbon in 6-ppd quinone concentrations in the water column? And did this differ across watersheds? So they're doing some filtering experiments along with their auto sampling. Next slide. And then USGS is leading work with WashDOT and working with us at Ecology to understand another priority question regarding how effective existing stormwater features are at reducing 6-ppd quinone. Most of the existing stormwater features were originally designed to control flow and or provide treatment for other contaminants. So some of this data will be used to inform a USGS 6-ppd quinone transport modeling effort as well on effectiveness. This work is funded by EPA and the National Estuarine Program. Next slide. And there are many exciting new projects starting up in 2026 with all these different partners. For example, a project to understand the impact to amphibians is starting. There's field studies. These field studies will provide environmentally relevant concentrations and exposure durations in wetlands areas, in urban areas. And there's at least a couple papers out now about amphibians, but the latest was by Sun et al. And it showed that there was negative impact to black spotted frogs, but very little information is available regarding the toxicity of additional amphibians. So two species that are regularly found in urban areas in the Northwest were chosen for some toxicity testing. So there's a field-based and a lab-based part of the project. And then lastly, next, we're on it. Yeah, 6-ppd quinone monitoring and research takes a network of partners and a mix of community and technical advisors. NOAA research partners are starting a new NEP project and plan to coordinate with our 6-ppd quinone coho salmon sentinel sampling network. Most of the research has focused on the Seattle metropolitan area, but we're hoping to do a project in Eastern Washington. And this is only mentions, some of the work being conducted around Washington. Additional exciting efforts are being discussed during the forum. And this is only some of our partners that I've listed here. So yeah, thank you.
Thank you, Rhea. We appreciate it. Up next is Bob Simons from Eurofins Environment Testing out of Australia.
Thank you, Tanya. Hopefully everyone can hear me and maybe not see me, but anyway, hear me.
We can do both, Bob. Thank you.
Yeah, look, thanks very much, Tanya and Heather, for reaching out. I'm going to change the sites to Australia. And just wanted to also thank the people that have done all of the hard work here. So Brian Wilson in our Brisbane lab and Amy Heffernan in our Brisbane lab, and also Andrew Patterson in the US, so who's going to be talking shortly. So I just wanted to give you a bit of geography lesson. So those of you who may have visited Australia may not have visited Perth, but Perth is one of the capitals, or it's a capital city of the state of Western Australia, and it's the most isolated capital city in the world. So it's about 2,000 miles from Sydney, if people have been to Sydney. So it takes about 4.5, 5 hours to fly. And it's got a greater population of about 2.5 million, although the capital itself is only about a million people. So it's tucked up here. It's got a really interesting climate, in that most of the rain falls in the winter time. So we're now a week into summer, and the samples that I'll be talking about are from taken in August this year. So that's in the middle of winter. So the temperatures in the winter probably are about 70 degrees maximum during the day, Fahrenheit, and they never get below about 15 overnight. But in the summertime, they can have extended periods, over 40 degrees, so over 100 F. So yeah, it's got a quite unique climate there. It is a very beautiful city. As I said before, there's about 1 million people located around here, but the black that you can see are the Swan River and the Cannings River. And a bit of a disclosure, to my knowledge, I don't believe we've got any coho salmon, but when this first came about, our emerging contaminants lab were quite keen to start measuring 6-ppd quinone. So this is the beautiful city of Perth, and as I said, most of the rain falls in the wintertime. In 2025, it had one of its wettest winters for 30 years. So sampling, we followed what's in US EPA method 1634. So we took grab samples. We also took the samples for tidal suspended solids, and we also took some samples for microplastics. Now, I won't talk about the microplastics work, but we're the only lab in Australia that is accredited to do microplastics, and that will be something we'll talk about a little bit later. But these are the sampling sites for tidal suspended solids. So yeah, these are all stormwater samples that are going into both the Swan and the Canning rivers. There is a field duplicate, which is FDO1, and there's also a blank in that mixture. So the methods we use, 1634. So, and I'm an analytical chemist, so quite interesting that we're also using isotope dilution mass spectrometry to get the gold. That's probably the gold standard to get the most accurate results. We've also done some work on a non-target analysis using high resolution mass spectrometry, and with the microplastics, we're using both vibrational spectroscopy and thermal analytical with the pyrolysis GCM-SMS. So just wanted to, the 6-ppd quinone we've been monitoring, but we also look at 2 other tire degradants, and that's the hexamethoxymethylmelamine, or HMMM, and the 1,3-diphenylguanidine, which is 1,3-DPG. So that's when we do our LCMS run, we also acquire the data for these other tire degradants. So as I said earlier, we're using the US EPA 1633 method. We're running both the D5 and the carbon-13 isotopically labeled standards, both for extracted internal standards and also non-extracted internal standards. And we use the deuterated DPG for the 1,3-DPG analysis, and we couldn't get an analog for HMMM, but we use that natrazine D4. We're using solid phase extraction, and we're using LCM-SMS to do the determination. So these are the results. So the y-axis is in microgram per liter, and I should have done it in nanograms per liter, but you can see here that the samples are pretty much the same as what has been previously reported today. So we've got a maximum here, almost 350 nanograms per liter, and that's the duplicate there. So obviously there's a little bit of a, with taking grab samples, you're not always going to get the same, but you've got levels that are over 50 nanogram per liter, and the texture limit's about 0.5 nanogram per liter. So, we're sort of, it's easy to find. But what I wanted to show you was this slide. So I've just overlaid the 6-ppd quinone. So the 6-ppd quinone is in the green, but the levels of the HMMM and the 1,3-DPG are extraordinarily high. So, you've got, sorry, this should be milligrams per liter, not micrograms. So these are levels that are like 10,000 nanogram per liter for the HMMM. So I'm not sure of the toxicity of these, whether they're going to be of any concern, but they may have a synergistic effect. Oops. That's my last slide. So yeah, it's got a bit squashed here, but what everyone's been saying is the acute aquatic toxicity of 6-ppd is well known. The runoff entering Perth's waterways could potentially cause some acute effects on the native species that we've got. It's, even though it's like a large river in a quite a large city, it still has got a lot of recreational fishes. So the impact we don't really know. And we've got some native Australian fish, so that's currently a major research group. So I appreciate everyone's time. Thank you.
Thank you, Bob. Next up, we have Haley Tomlin from the British Columbia Conservation Foundation.
Thanks, Tanya. Hi, everyone. My name is Haley Tomlin, and I'm a biologist with the British Columbia Conservation Foundation's Aquatic Research and Restoration Center based in Nanaimo, British Columbia. Our office undertakes a variety of different research projects, including stock assessment, habitat restoration, and water monitoring projects across Vancouver Island. And I'll be touching on some of the 6-ppd quinone monitoring that we've been doing in partnership with Vancouver Island University's Center for Health and Environmental Mass Spectrometry. So just to get you oriented with where we are, since we just came from Australia, we're back in Canada now. We're located on the west coast here on Vancouver Island. Specifically, we've been working on the east coast of Vancouver Island, as this is where all the major urban centers are, and about 90% of the island's population is located between Campbell River and Victoria. Let it load. There we go. So our monitoring program has two primary objectives, the first being what and where are the major sources of tire toxin impacts on Vancouver Island, and the second being how do these concentrations change over time and space. I'll be focusing on this first objective, and my colleague Eric will be sharing some of the monitoring that we've been doing that's focused more on the higher frequency sampling in the presentation that follows mine. So to begin understanding the extent of sampling required, our team first looked at all the locations where roads and salmonid-bearing streams intersected. And in that about 300-kilometer project boundary from Campbell River to Victoria that I mentioned, there's over 10,000 potential sampling locations. So with so many road creek crossings, our team realized we needed a quick and cost-effective means to run thousands of samples if possible. And we also realized with so many microclimates and variable weather patterns, it's for us to undertake the sampling in an effective way, we would need to have sampling crews across the east coast of Vancouver Island. So first, to assess our ability to take on a large quantity of samples, VIU tested their condensed phase membrane introduction mass spectrometry, or CP-MIMS, which Eric can definitely speak more to than myself, but to see its ability to detect 6-ppd quinone. When compared to the conventional LCMS method, CP-MIMS has proved to be a direct, fast, and effective an extremely cost-effective means for analysis. So prior to expanding any sampling efforts, we used CP-MIMS and LCMS and ran duplicates, and CP-MIMS was proving to be an effective means to measure 6-ppd quinone. And although very efficient, it still required someone to stand at the mass spec all day and swap samples out one by one. So to solve that problem, one of our previous graduate students, Joseph Monahan, retrofitted a 3D printer as an auto sampler. And this streamlined process allowed for 25 samples, 5 control samples, and calibrations to be run within 3 hours. So this was allowing for around 100 samples a day, depending on how much time the students were willing to put in that day, which they're very dedicated, so long days usually. And then thankfully, funding was acquired for a second mass spec through the Pacific Salmon Foundation, and this allowed us to run over 100 samples per day. So with the analysis bottleneck out of the way, we needed to be prepared for a large number of samples from volunteers. And Joseph came to the rescue with that again. And to simplify the data collection and limit data transcription errors, he developed a data collection app. So this uses unique QR codes on each of the sample bottles and then QR-coded sample locations for each site, ensuring that the sites that we were revisiting regularly were labeled the same each time. We also had photos taken each time we collected a sample to help with the QA/QC. And beyond the auto sampler and data collection app, he also created some data processing programs that helped with the assistance of inventory in the lab and some quick visuals of results. So as mentioned, we realized we needed a lot of sampling crews up and down the island to accommodate the variable weather patterns and microclimates. With that, we recruited volunteers from local First Nations and community-led stewardship groups across the island. These groups assisted with site selection and sampling within the region. It was my role to watch the weather and coordinate the sampling efforts around storm events that followed some dry periods. Our initial sampling efforts began in 2022 with about 10 groups and quickly ballooned in 2023 to about 32 groups with funding from the BC Salmon Restoration and Innovation Fund. In total, 37 groups and of over 150 volunteers have been trained and engaged in the sampling efforts in this program. To begin, most groups targeted a single location, but as we've moved through the years and have realized how site-specific concentrations can be, volunteers have been adding sites within their watersheds to work towards identifying the most harmful inputs. Overall, since September 2023, our crews alongside the volunteers have collected more than 6,600 samples, largely through grab samples and auto samplers. These samples have spanned 22 rain events, 73 streams, and over 180 sample locations. We've been collecting samples before, during, and after rainfall, and finding that 6 ppdq concentrations are above the BC's acute water quality guidelines of 10 nanograms per liter in about 26% of our stream samples collected. The largest portion of our samples that had concentrations over 10 nanograms per liter were those collected during the rain rather than before or after. In addition to the stream samples that we've been collecting, we've also been collecting samples directly from point sources, so downspouts on bridge decks or outfalls, wherever possible, and these concentrations have been typically about 10 times the concentration that we've been observing in the streams. Some of the main data findings, I'm going to focus more on the spatial stuff as Eric's going to be talking about some of the more high frequency stuff. The first thing is that the timing of grab samples really matters, as we've seen in a few different presentations. The concentrations are really dynamic, which raises a lot of questions about how representative grab samples are and how many are required to accurately depict the full 6 ppd quinone dynamics within a waterway. The second takeaway we've had is that results are highly site-specific. Therefore, sampling in many locations along a single waterway is important for identifying the most impacted locations and where mitigation is most needed. So a few examples of this higher spatial sampling is along this right-hand side of the screen there. So in particular, the Cat Stream in the top box and the Chase River and Wexford Creek in the middle box are a few of the systems in Nanaimo that we've had some good spatial coverage on. In particular, the Cat Stream, we have 16 sample locations on the Cat Stream, which is a small waterway that runs through a residential neighborhood and supports both coho and cutthroat trout. We've seen concentrations above 300 nanograms per liter at 2 of the sites in the upper reaches of the watershed, which are both downstream of very obvious inputs such as large parking lots and large catchments from steep and very well-used roads. There's a university and high school that kind of run adjacent or right over the Cat Stream, so there's lots of traffic there every day. We've also seen other significant inputs equal to or greater to 100 nanograms per liter in different locations throughout the watershed as well, so that's going to help direct where we're going to aim to do some mitigation down the way. Our third takeaway is that the smaller urban streams are observed to have the highest concentrations along the east coast of Vancouver Island. And lastly, the first flush, or the idea of a first flush being a once-a-year event in the fall, is not necessarily true. These long dry periods at any time of year can have the same effect. We saw in the first year of sampling where we actually kind of saw our concentrations decreasing through the season. But this last winter, we actually saw our highest concentrations ever for most sites in January 2025 after approximately a month-long dry period. And then these screenshots are from a data dashboard that's publicly available, which I've managed to forget to include the link on here, so I'll share it in the chat afterwards, just so that anybody that's interested can kind of noodle around and see what we've been finding. And then, as mentioned, we've been heavily dependent on volunteers to collect the samples outside of Nanaimo, because that's where we've been doing our sampling for the most part. And without them, we wouldn't be able to have the geographic coverage that we do. That said, some of the takeaways from working with the volunteers for this type of program, the first thing is that preparation is key. Having streamlined processes and systems to reduce transcription errors and lost data are critical. This is also true of doing the inventory and management of samples in the lab as well. And then additionally, there is many benefits just to engaging the community and having citizen scientists on board. So these groups know their respective waterways very well, and they can help inform site selection. Specifically, they know where it's safe to access, where they've seen anything of note previously, and then they also have a lot of pre-existing relationships with private landowners, which has allowed us to do some sampling in locations that we might not have otherwise been able to do. They can provide really quick response times to last-minute sampling. And engaging them early on, we've been finding that they're really keen to help with the implementation of mitigation strategies later as well. In general, it's just a great education opportunity. So with that, I just wanted to say that this project wouldn't be possible without our partnership with VIU, as well as all those 37 engaged First Nations and community-led stewardship groups. And further, and obviously, we wouldn't be able to do this without the critical funding from the BC Salmon Restoration and Innovation Fund, as well as significant contributions from the Pacific Salmon Foundation, MyTax, and the Regional District of Nanaimo. Thank you.
Thank you, Haley. And our last presenter before break is Eric Krogh and Angela Yeager from the Vancouver Island University. So Eric and Angela, whenever you are ready, you can take control of your slides.
Hi, thank you, Tanya, for the opportunity to speak with you and the group today. And thanks, Haley, for such a great setup. I'm going to, so my name is Eric Krogh. I'm a professor of environmental chemistry here at Vancouver Island University. And I work with the BC Conservation Foundation. So Haley Tomlin is a key member of our group. And the work I'm going to talk about today involves looking at how we can leverage that high throughput analysis that Haley introduced you to answer some other questions that are quite sample intensive. So our group is run by two graduate students, former graduate student Joseph Monahan and Angelina Yeager, whose claim to fame is, I think, as an individual, has run more 6 PPDQ analysis than anyone else on the planet. And you'll see a number of other undergraduate students that are listed here, as well as my colleague Chris Skill, who's the co-director of the Center for Health and Environmental Mass Spectrometry, along with myself. And then Jameson and Haley are with the BC Conservation Foundation. So just a quick recap of the technique we use. It uses a semi-permeable membrane that acts as a direct interface to introduce samples into a mass spectrometer. So we use polydimethylsiloxane, which is selective for neutral hydrophobic analytes, essentially anything with a log KOW greater than 3, so fairly hydrophobic. And it provides us with a simple workflow for doing high throughput analysis and even real-time measurements. You'll see a little schematic here, which shows our capillary hollow fiber membrane mounted on an immersion probe that's dipped directly into our aqueous sample. We add some internal standards for quantitation to both the aqueous sample as well as the solvent that's flowing through and go into our mass spec. So this allows for a simple workflow with sensitivities down to 1 nanogram per liter. And we have some selectivity at the membrane level as well as the ionization level. We use positive mode ESI. And then, of course, we have tandem MS experiments for each of our target analytes. So we look at 6-ppd quinone as well as structurally related quinone analogs. This allows us to get samples all the way through the complete analytical duty cycle in 2.5 minutes without any pre-treatment other than adding a spike of an internal standard. And this also allows us to make some time resolve measurements. Haley mentioned their agreement with LCMS, so we also run liquid chromatography MS, which is the gold standard, and we do measure a subset of our samples with LCMS and monitor that level of agreement as we go. So we've talked a lot about some large scale variations up and down Vancouver Island. I want to zoom way in here. This is just looking at downtown Nanaimo, British Columbia. Nanaimo is a mid-size city, population of about 100,000, and if you include the surrounding communities, around 200,000. So certainly not anywhere near the size of Metro Vancouver or Seattle or the Seattle-Tacoma area. So this is a hyper-local look at the Cat Stream and the Chase River in close proximity to the university where I work. I was going to say live and work. I only live here some of the time. And we see some very high degree of spatial variability, even on a distant scale of 100 meters to a kilometer along the same water course. And so this, of course, raises some important questions. If time is so important, how does it move through the system? And so we did something called a simultaneous sampling. So we got a bunch of volunteers and we got out and we all filled bottles at the same time at different locations. And we saw concentrations ranging from no detects up to over 100 nanograms per liter on that one particular day. And if you look at this structural variability in terms of what's going on under the ground, and we zoom in on the stormwater infrastructure, each of these circles that are showing up on the Cat Stream and Chase River are outfalls for stormwater outflow into those receiving waters. And so it's very complicated, and it's much more than just what's running off the surface into those creeks and rivers. In fact, the largest influence that we observe is from these underground stormwater outfalls. So that explains quite a bit of the spatial variability, at least in a urban area. And I should say that that last slide I showed you was in a heavily residential area, not particularly high traffic or particularly high speeds of travel. The other thing that we wanted to look at was the time dependence of these concentrations. And so I'm, again, zooming in on just the central part of Vancouver Island and the Nanaimo area. And we're looking at 3 different streams. So first we'll start with the Northfield Creek, which is shown here in red on the map, and the time series also shown in red as well. And so that's Northfield Creek, which is a highly urbanized, highly impacted urban stream, which has basically been buried underground and has a lot of stormwater inputs. On this time series, you'll see 6 ppdq concentrations ranging from 0 up to 300 nanograms per liter. And that's shown for Northfield in red. The shaded area that you see there has to do with the fact that since it's so easy for us to run replicates, we run all of our detected samples 3 times. So that shaded area represents 1 standard deviation on that triplicate set. Also shown on this graph is the rainfall coming down, and that's precipitation in millimeters. And so you see a relatively small rainfall initially. This was on November 30th of 2023, and then some moderate rainfalls, and then a big rainfall coming about a week later. So we were out doing intensive sampling across this series, and you see very high concentrations, but also very, very dynamic changes, especially at Northfield Creek. If we then look at another creek system, Millstone. Millstone is a larger water course. It runs through town, through a lot of green space. There's a beautiful park along the Millstone, and it's shown in green, but on the time series, it's just barely above a detection, so barely above a few nanograms per liter for us, and well below the BC water quality guideline of 10 nanograms per liter. If we then have a look at the Cat Stream, we see that We at detectable levels, also very dynamic, but not nearly as high concentrations as Northfield. Although it was exposed to the same rainfall, it's only about 1 kilometer away from the Northfield Creek. You do see a delayed onset of those concentrations, and this has to do with the hydrology, has been mentioned by several other speakers. We've also been looking at taking our mass spectrometers out into the field because we can do this sample analysis in real time. And so we actually parked our vehicle, our mobile lab, with our mass spec near a stream. This is the Chase River, not too far from campus. And we pumped stream water up to the vehicle and then passed it through this flow cell, if you like, with our membrane immersed inside. So basically, we're making measurements on site in real time as that stream water is passing through our mobile lab. And so when we look at the data that results from that, you'll see here in green, this is 6 ppdq concentration shown, again, with the rainfall coming down from the top. The blue dotted line that runs horizontally across here is the discharge from a rating curve that we worked up so that we can figure out what the total flow of water is in the creek. And so this data represents the first real-time measurement of 6 ppd quinone on site during a rain event. That's Angelina, happy that all that effort paid off. And we also wanted to check this against some discrete grab samples, and so we could modify our in-field calibrations, and then we did that with some auto samplers that you've heard about earlier today. So a couple of other things that we've done is we've looked at the real-time leaching kinetics. So this is Lily and Nikki, who've done some great work looking at street sweeping sediments, basically road dust, and monitoring the concentration of 6 ppdq that's coming off on exposure to a pristine deionized water sample. And we see those concentrations come up within minutes and continue to rise for several hours depending on the sample. Test shown here in this bottom left-hand quadrant is looking at sorption kinetics, so looking at different sorption materials in real time and showing that some biochars and organic carbon are very effective. And we've also done some phys-chem property analysis of the 6 ppd quinone analogs with some great work done by Misha, as well as some leaching of some end-of-use tire products such as crumb rubber and tire mulch that Erica Sorensen has been doing some great work on. And one of the things that we observe there is that when these compounds leach off of this tire rubber, if you clean them after they've reached equilibrium and you refresh that water, you get more 6 ppdq coming off in those subsequent washes. So we also did a project with the city of Victoria in the Capital Regional District, the south end of Vancouver Island, working with their grounds crew to figure out how to collect street sweeping samples and catch basin samples. And we've been measuring concentrations in these equilibrated aqueous phases, but we've also measured the concentrations in the total mass as well. So we would have the dry weight of these materials, and we look at what comes off leached into water within the first couple of hours. And then we also do the total concentrations. And the takeaway here is that what's in the aqueous phase is actually just a small fraction, usually less than 5% of the total mass of 6 ppdq that's in that sample and unavailable to leach in subsequent leaching.
Hi, Eric, are you able to wrap up your presentation within the next couple seconds? Thank you.
Sure. I'm just going to skip to the end here. What we've learned is that there's a lot of variability over time and space. About 70% of the urban stormwaters are above the BC water quality guideline. And small urban streams heavily impacted. And we see that in some cases it's transport limited and others it's mass limited. And it's well predicted by the dry days preceding and the turbidity. And one important takeaway is that these tire particles can act as recurrent sources of 6 ppdq in the environment. And with that, I will wrap up by acknowledging all the great people we work with and the funders. Thank you very much for your attention.
Thank you, Eric. I appreciate it. We are going to go to break. We will be back at 2:10 p.m. to continue with the lightning talks. All right, welcome back from our 10-minute break. In order to keep with time, I'm going to go ahead and introduce our next presenter, Kirsten Maxwell from the University of Washington.
Hi, I'm Kirsten, and I'm a graduate student at University of Washington. And we've been working on a project focusing on detecting tire chemicals in Puget Sound tire reefs. These tire reefs have been installed since the 1970s, where the purpose of their installation was to provide habitat and attract marine life in Puget Sound. It's supposed to be a video, Tanya. I know that might have been a problem. So these tire reefs were installed as habitat, and they've been used as habitat, as recreational dive sites, and study sites of the inhabitants. And more recently, in 2024, 2025, this ongoing process to remove them has taken place across Puget Sound. There are 14 reef removal sites where the Department of Natural Resources is removing these large tire reefs. And for this project, we're focusing on 3 tire reefs. I'm sorry with the image there. So the tire reefs that we're focusing on are in Hood Canal, Des Moines, and Edmonds. With this project, we have the goal to see if tire chemicals are a concern and if they're present in these old tire reefs. And we want to quantify the tire chemicals in seawater from the tire reef, in sediment from under the tire reefs, and from the rubber from the tires composing that tire reef. And we started sampling about a year ago to sample these 3 tires, sediment, and seawater from each of the 3 study sites. For our methods, we have been using solid phase extraction for all of our aqueous samples, which includes the tire leachate and the seawater we collect. And for our sediment, we use a solvent extraction, and then both of these are run using LCMS triple quad analysis, and we target a whole suite of tire and vehicle chemicals to detect for them in these samples. So when we take a tire out of Puget Sound, we cut off a chunk of the rubber and the piece of tire, and we put it in seawater from that site. And then it leaches over time. And the samples in this figure have been leaching for 5 months, and we're analyzing that aqueous extract. And what the data indicates is that, certain tires have a bunch of chemicals, and we suspect that the surface area we introduced by cutting the rubber and submerging it in that seawater introduced rubber surface area for the chemicals to leach out of. And likely this chemical mass came from cutting the tires, but it is indicating that these chemicals are present in the rubber. And they do have the potential to leach if given that surface area opportunity. But we suspect not much chemical is moving out of the rubber from the tires in the reef, those uninterrupted tires that we've not cut. This is a transport limited situation with the chemical coming out of the rubber, but we do see that these chemicals live for a long time in the rubber from the tires in the reefs. And the concentrations of leachate and in a couple of slides in the seawater, the concentrations of chemical are much lower than we see in urban impacted streams from those inland sampling efforts. Overall, we are seeing the chemicals are present, but we suspect that there is not urgent concern that they are leaching from tires in the reef. In our sediment samples, we noticed that there are PPDs present in the sediments, more so than their transformation products and then quinones. And these PPDs, as you can see, the blue bars are from actual reef sites and the gray bars are control sites. And so we notice that there are more chemicals, more PPDs in the reef sediment than there are far away in the control sediment sites. But overall, these chemical detections are low when we compare them to rubber. And so rubber would have, from 6 ppd quinone, it has around 15 microgram per gram of 6 ppd quinone, and these have, tens, 100 level lower than rubber, and in 6 ppd up to 100 microgram per gram in rubber. So these sediment detections are trace levels, especially when comparing it to actual tire rubber. But we are able to notice they are detected in reef sediment, and even more so than control sites too. When we looked at the reef seawater, so this is water that is collected down in the tire reef between the tires, and this is just seawater grab samples. We were noticing low concentrations of tire and vehicle chemicals, and like 6 ppd quinone is lower than 1 nanogram per liter in this water. So we're again hinting at an aqueous pathway is not as much of a concern, but there could be a concern for organisms that are living on the tire and have chronic exposure. There are unknown implications there that we're investigating. We do notice from the data that the benzotriazoles and the DMBA are at high levels in both the water from the reef and the water from the control site. So there may be these background levels of tire and vehicle chemicals in Puget Sound water, regardless of if you're sampling at a tire reef, and implications there for the backgrounds in Puget Sound overall. Our conclusions so far on this project are from our leaching study. There are chemicals still present and able to leach if given the opportunity of exposed rubber in these 1960s, 1970s tires, including 6 ppd and 6 ppd quinone. The seawater has low to no concentrations of 6 ppd and 6 ppd quinone, and being low in the seawater and low in the leaching, we suspect that there is not much leaching from the actual tire reefs in the environment. In the sediments, we were seeing PPD compounds more so than transformation products and PPD quinones, noticing that these PPDs are more commonly detected from the reef sediment than from control sediment sites. Our future work includes longer-term reef sampling using a POCES sampler so we can get that our detection and our exposure time longer and better detection. We also would like to include, we will include toxicology exposures to supplement these concentrations we're finding and be able to explore the exposure to organisms to better understand what's happening in the actual environment of these reefs, and that is with Washington State University. And then we're also working on doing rubber profiles for each of these old tires and seeing what's actually in that rubber. And then I would like to thank everyone involved in this big project, and our funding sources are there as well. Thank you.
Thank you, Kirsten. Up next, we have Stephanie Gordon with the United States Geological Survey.
Hi, can you hear me all right?
Yes.
Great. Yep, as she said, I'm Stephanie Gordon. I am with the Eastern Ecological Science Center out in West Virginia. And not sure if I'm the only East Coast person, but I'm going to be talking about the work we've been doing to develop a national 6-ppd quinone heat index and web map tool. The two people listed on this slide are the co-leads for this work, and definitely not the only people, but they are also the co-leads of this geospatial lab that I'm just going to mention briefly. Give a little background on this lab because the methods I'm presenting, we also apply across multiple projects from HABs to mine lands to endocrine disrupting compounds. And our focus is on using geospatial methods to identify known and suspected sources of contaminants on the landscape, and then linking those to different end members. And we're really focused on developing risk assessments and making predictions at multiple scales, with the goal of understanding the landscape and understanding its role in environmental health. In particular, we started working on 6-ppdq in 2022 when some USGS coworkers in the Pacific Northwest were trying to prioritize sampling locations in and around the Puget Sound. This map on the right was a pilot effort to map the known and potential sources at the time against known coho salmon streams. And these are kind of summarized within our USGS stream gauge network to help our, it was John Hansen out there, prioritize sampling sites for stormwater work. So as we were going through that process, we wanted to expand and see if we could make this national risk layer to address 6-ppd quinone and potential exposure. So this is just a basic slide that's an overview of the process as a whole, and then I'll dive into some of the specifics. But basically, we selected data sources on what we knew and what we theorized were potential sources of 6-ppd and 6-ppdq on the landscape, and a bunch of other basin characteristics that might influence delivery to the streams. So these were cleaned up and summarized at a small watershed scale, which is the NHD plus version 2 scale. It's a 1 to 100K catchment, so pretty small watersheds. And then values after summarizing were scaled from 0 to 1, and weights were applied using some of the 6-ppdq experts that we know because we're geographers. We know a little bit about a lot of things, but not a lot about any one subject. So we tapped into our 6-ppd experts to weight some of these inputs and summed the values to develop a final relative heat index that we could look at against where species might be, species of interest might be on the in the streams and on the landscape. So the sources that we decided to include in our heat index were gathered from a couple different places. We used the US Census Bureau roads database we removed any like pedestrian roads and then used their road layer to calculate the total length of roads and the number of road stream crossings per small watershed. We also then used traffic density from EPA. They've been developing a bunch of water quality tools, and that was included in one of them. Used Department of Transportation for information on the location of truck stops, and then used another EPA data set to identify tire handling and rubber production facilities and where those are located. And finally, the airports layer from the FAA, from the Federal Aviation Administration, was used to calculate the area of runway by how busy the airports are. So they were binned into different types, how busy the airport is, what kind of traffic it is, what kind of landing strips are there, as much detail as we could get into. The landscape characteristics that were relevant to our final heat score were runoff, the average annual number of dry days in between precipitation events, slope of the catchment, and then average imperviousness calculated for each of those small watersheds. And then just throwing again that we have fish presence, but it wasn't tallied into that heat score. The final step was weighting the different sources that I mentioned. So these summaries of all the raw data were scaled and multiplied by increments to account for more or less relative expected impact on 6 ppdq delivery. So you can see things like primary roads and secondary roads that get a lot of traffic, and large airport runways. And then our basin characteristics were kept static. Those were given a weight of 1. And then smaller roads, small alleys, off roads, tiny airports that might have grass as a runway, or regional airports were given much lower weights. So the result of this work is 2 products. So first, there's a public data release, which is linked here, and I can share around as well. So this is tabular files with unique IDs to link to the spatial data. So the tabular files can be downloaded, and then locally you can do analysis and map, or however you want to use that data. And the second product is, an online interactive web tool. So the homepage is shown here on the right-hand side of the screen. This gives a little background on the work and an overview of the steps that I went to, and links as well. And the second page, I'll show the mapping dashboard itself. I want to take a second to make sure that I acknowledge this is the 6PPD Brain Trust, John Hansen, Rachel Lane, Justin Greer, and Kelly Smalling, who are all USGS. And then there were definitely folks who were on this call who were extremely helpful in helping us develop this. So this is what the map side of the web tool looks like. The heat map is shown in this kind of green to blue teal scale. It covers the entire lower 48 states. We're just zoomed into Washington State for now. There's a tour you can click through in the top right that'll show you how to use this. There's tools to access Legend and add your own data or sample sites, basically whatever data you want to add, stuff from the web. We did get feedback early on from some collaborators in the Delaware River Basin that being able to query all of the data that went in, so the raw values, the scaled values, and the final heat value, was most useful to them. So we made sure to include these custom filters that you can set up inside of the data tables. And there's a separate pop out to learn how to do these custom filters. They might be a little tricky. Send us an email if you're using this application and you want to walk through it at any point. We are always happy to help. Oops. Oh, well, there we go. Sorry, it's a bit delayed. There we go. There are, of course, pop-ups. If you just click on any given watershed, you can see how small that is in the kind of lit up blue area there. It gives a report of the information at the top and indicates if there are flags for if the raw data was incomplete or inconsistent, and there's a lot of detailed information on that on the homepage and in the data release as well. This is an example of those predicted fish layers. We used this mapper and we used locations of brook trout that were known brook trout streams in the Chesapeake Bay watershed over here on the East Coast to identify some sampling locations for work out here. This is a modeled fish layer, and again, you can add data if you have more local detailed data that would be more useful to different analyses. This is so you can get kind of a quick assessment of if there are species of interest predicted to be present. Finally, as you all know, there's always caveats with data, and especially big data at the national scale. Mostly, we are aware that the traffic layer is not consistent across catchments, and you might be able to see on the right-hand side here, there's 2 adjacent catchments where one has a traffic of 0, and the second has a traffic count of 90,000. Of course, there's probably traffic in both places, but this is due to the way that it was collected and upscaled, and traffic data is kind of very messy to work with. So when we're talking about moving forward with this layer, we really want to be cognizant and incorporate local, more consistent data into areas that are going to be useful for people. for scientists, people using this to prioritize sites or whatever. So we're starting with a pilot effort in the Chesapeake Bay using the sample design results from that initial effort to help refine and explore where higher resolution data for traffic and things like tire dumps could be used to improve our heat index. Preliminary results from that are showing a lot of agreement between the heat score and the measured concentrations, and we're hoping to share that and improved versions of the data and tool in the near future. And our contact info is, oh gosh, on the last slide, which I skipped. There we go. Thank you.
Excellent. Thank you, Stephanie. And next up, we have Mallory Little with the Washington State Department of Health.
Thank you, Tanya. Hold on. All right. Hello, everyone. My name is Mallory Little, and I'm a toxicologist at the Washington State Department of Health. This lightning talk will give you a brief overview of what we know about 6-PPD, 6-PPD quinone, and human health. There's a lot of information on these slides that I don't have the time to cover verbally. So if you're interested, you can go back and view the recording to read the details on the slides. So far, the main focus of the scientific community has been on the ecotoxicity of 6-PPD quinone. Department of Health toxicologists, however, have been tracking the human health-related research of both 6-PPD and 6-PPDQ, while accounting for the wide variety of exposure pathways of people to these tire chemicals. First, I will give a brief overview of the hazards of the parent chemical. 6-PPD has been in use long enough for organizations to determine hazard classifications for several health effects, and multiple studies in animal models have characterized its toxicity as well. It's established that 6-PPD causes skin allergy, particularly in people who are allergic to other paraphenylene diamines, and 6-PPD is also suspected to cause respiratory allergy as a follow-on to the skin sensitization findings. 6-PPD is also a suspected human reproductive toxicant due to multiple animal studies, including one that found dystocia in rats, which in this study was abnormally prolonged labor that resulted in the deaths of both the mothers and the pups. Moving along, 6-PPD is also associated with fatty liver disease, according to one study in people. Liver damage biomarkers are also well replicated across animal studies. 6-PPD has also caused anemia in multiple animal studies, but we don't know if this occurs in humans. Other effects like developmental and intestinal toxicity are being explored in animal and in vitro studies. A common theme across the research for many of the health effects I've just described has been that increased oxidative stress caused by the overproduction of reactive oxygen species from exposure to 6-PPD is the mechanism for many of these effects. Overall, it's clear that 6-PPD is a concern to human health, which should be considered when figuring out how to address 6-PPD quinone. Now on to 6-PPD quinone. There have been many observational studies in which researchers looked at levels of this chemical in the bodies of people with various diseases. For example, higher levels of 6-PPDQ have been found in disease cohorts of colorectal cancer, Parkinson's disease, and polycystic ovarian syndrome patients compared to controls. A couple of liver studies in people have found higher levels of 6-PPDQ in the serum of people with fatty liver disease than healthy counterparts, and more liver lesions were observed in outdoor workers with higher levels of 6-PPDQ compared to indoor workers. Unfortunately, most of these studies didn't look for other tire wear particles in the bodies of these cohorts, and also it's not clear whether the diseases are causing increased 6-PPDQ or vice versa, so causal inference is limited. Toxicity has also been shown in animal studies, which strengthen the human findings. For example, with liver studies showing altered enzymes and metabolism. Reproductive and intestinal toxicity are also being explored in animal studies, such as with intestinal barrier disruption and inflammation being shown in multiple model organisms. As with 6-PPD, oxidative stress and also barrier disruption are being explored as potential mechanisms for many of these effects. And while there are many commonalities with the effects of 6-PPDQ to 6-PPD, there are some distinctions as well, with no or limited findings of anemia and skin allergy being found for 6-PPD quinone. Innovative research methods that don't involve animals have been employed recently to look further into 6-PPD quinone. For example, EPA recently published the results of a suite of high-throughput assays showing 6-PPD is more bioactive than 6-PPD quinone. None of these studies, however, produced a reference dose, which is needed to compare against the exposure that humans receive from the environment to characterize the true risk of these chemicals. Included on this slide is a figure from Xu et al. Showing points of departure for 6-ppdq in intestinal and liver cells compared to environmental occurrence in human biomonitoring data. But because these aren't reference doses, this is not a true risk comparison, but it does provide some context. As I've alluded to already, both chemicals are widespread in people's bodies, particularly in studies of blood and urine taken from people in China. We don't have data for United States populations yet, but 6-ppd is used in tires all over the world, so the Chinese data are relevant. Both chemicals have also been found in breast milk and umbilical cord blood and other diverse compartments such as amniotic fluid and placenta for 6-ppd, and cerebrospinal fluid and ovarian follicular fluid for 6-ppdq. But the question is, how are these chemicals getting into people's bodies? So the next 4 slides show exposure pathway diagrams, and all of them look for the pink dots, which represent 6-ppd and 6-ppdq. These pictures are available on our webpage if you want to look closer, and I will provide a link to this page at the end of this talk. Here's an urban landscape that shows the 2 chemicals coming off of tires and being washed into nearby water via runoff during rain. A few studies have found both chemicals in edible fish tissue in China, and the Department of Fish and Wildlife is looking at a small pilot study of 6-ppdq in salmon. So because of this, we are concerned about eating aquatic species from waters with high tire particle occurrence as a potential route of exposure. We're also concerned about aquatic plant uptake of these chemicals, but we don't have any data on this yet. This graphic also highlights that people rely on fish for subsistence and to sell, showing that the effects of these chemicals on fish can hurt people indirectly as well. Now we're looking at a family indoors. In this diagram, we've highlighted inhalation of air and dust as exposure pathways. This dust may be coming from consumer products such as rubber mats and sneaker soles, which can contain 6-ppd. Young children are more vulnerable to this exposure due to contact with the dust on the floor and hand-to-mouth behavior. We also see road dust or air with 6-ppd and 6-ppdq floating into the home, which could be an issue, particularly if the home is near a busy road. 6-ppd, but not the quinone, has also been found in tap water in New York, and both chemicals are in drinking water in other countries, but we don't know of any sampling of water in Washington. There have also been studies showing these chemicals can be present in leafy greens and other produce. Here we have a more rural scene. We know crops can contain both chemicals, but we don't yet have enough data to know if this is from road runoff, air deposition onto crops, or through biosolids and other soils. This diagram also shows that people who work near roads might be more exposed. A recent paper found higher levels of these chemicals in the bodies of outdoor workers compared to indoor workers. We're also concerned about people who work with tires. For our last diagram, we show people using an artificial turf field. We know that these fields contain 6-ppd in the crumb rubber used to amend the fields. Ecology is currently studying runoff from turf fields as well. So people playing sports or using a playground or other activities on these fields may contact these chemicals in the crumb rubber. Hand-to-mouth behavior can also be a pathway for young children on turf. Lastly, we've also included a car in the image because studies have shown these chemicals in the dust inside vehicles. While not the main focus of this talk, I want to mention the indirect effects of 6-ppd on people. 6-ppd's harms to salmon populations can affect people's well-being in other ways than the direct health effects as well. The declining health of salmon and other aquatic life can harm the holistic health and lifeways of people who rely on these species for food, spiritual and emotional well-being, community health, and economy. There will be a great breakout session on community advocacy later today that will highlight these issues. So in summary, we know that these chemicals are not staying in tires, but are present throughout the environment and have been detected in multiple parts of people's bodies. Both chemicals are associated with several types of disease in humans, but we don't know if this is correlation or causation. And we also don't know if other tire wear chemicals play a part in this as well. There's also supporting evidence from animal models for a diverse array of organ toxicities from both chemicals. Overall, we consider both 6-ppd and 6-ppd quinone to be a concern to human health in similar and different ways. So Eleanor Fanning and I will be discussing data gaps in human health more this afternoon in our breakout session, so make sure to attend if you're interested. But in short, we don't yet know if levels of these chemicals are high enough in the environment to be directly toxic to people because we don't yet have a reference dose. We also don't have any biomonitoring data for people in Washington state or the US as a whole, so we don't know how applicable the research from other countries is to our exposure. And we also don't know how much people are affected by the indirect health effects from 6-PBD on fish decline. Briefly here, I'd like to give a shout out to the Department of Health 6-PBD team. We're all here today leading breakout sessions. And thank you so much for your attention today. You can reach our webpage by scanning the QR code here. If you have any questions, you can email our team at this address or come to the breakout session later, and we'd love to address them. Thank you.
Thank you, Mallory. Up next, we have Andrew Patterson from Eurofins Environment.
Good afternoon, everybody. My name is Andrew Patterson. I'm the VP of Innovation and Development here at Eurofins. I'm trying to advance the slides. We're going to be talking serendipitously right after that wonderful talk on determining potential mass transfer of 6-PBD quinone from a roadway to hands via basketballs. So I'm very keen on biomonitoring, and so this could be an exposure pathway for 6-PBD quinone. So I'm really excited about this conference, and I was thinking about like, what should I do that's a little bit different? And then I heard my kids arguing outside. I live on a cul-de-sac in Northern California, and I heard my kids arguing outside about basketball, and I thought, well, I wonder, and I do love when you can use science to answer a very specific question with a whole lot of analytical firepower. I wonder if there's any 6-PBD quinone ending up on their little hands. So I should add that first that 6-PBD is not 6-PBD quinone. Everybody in this talk likely knows that the 6-PBD is the parent compound that is added to tires, and 6-PBD quinone is the product after exposure to ozone that sloughs off and ultimately ends up in creeks and streams and roadways, and that's why we're all here talking. And so the focus definitely is on 6-PBD quinone, but I think as we get into things like air matrices, that 6-PBD, the parent compound, is going to be a significant part of that discussion. So what did we want to do here today? Well, the idea is simple. We had to find a basketball that doesn't have 6-PBD quinone on it. We have some players that wear background-free gloves, play some basketball, and during that process, we're taking different wipe samples. The wipes that we use are a simple gauze that we know doesn't have any background. We're using a little bit of acetonitrile as the solvent. Everybody that's doing 6-PBD quinone analysis understands that acetonitrile is the key to success. We would much rather use methanol, but that's just not the case. We need that extra extraction power of acetonitrile. So we're going to be taking different wipes kind of before, during, and after play. And then we put those wipes all together in an analytical run through that I'll show you here in a second. And we see, is there mass transfer from the street to the ball to the road? So spoiler, here's our test crew. We actually had to delay testing because we were getting nothing but rain in Northern California, which is very much needed for the fire season and the ski season, and just in general. But we had to delay our sampling. So what we are looking at here is 4 days after the last rain event. I talk about that later on a slide, but we actually had to wait for a dry period, and now it's been nothing but foggy. But this is a very controlled environment, as you can see. We've got some neighborhood kids, including my son, that volunteered to play some basketball. So the time period was a half an hour. So we had this brand new basketball that we knew was background free. Please put on these gloves, play as you normally would play, and then we're going to take some different sampling after the fact. So in a nutshell, how did we do this? It's an adopted 1634 workflow. All this analytical work was performed at Eurofins Sacramento. This is where the method development occurred for EPA 1634. We're getting a lot of mileage out of that, and we're very enthusiastic about that. So we would spike in the 13C6. This is the EIS from the method, directly onto that wipe. It undergoes a serial sonication before dilution in water and subsequent solid phase extraction, or SPE, just like a 1634 aqueous sample would be at that time. After extraction, we add the NIS, or the non-extraction internal standard, And if everything goes well, we see both the isotope and detections if they are present. So general workflow looks a lot like 1634. So what did we find? Drum roll. Well, we found that lo and behold, when you play on the street, your hands look a little bit like the street, and that brand new shiny basketball looks a little bit like it's been used to play street basketball. And those are some of the items that we wiped in our study. So all the results, here we are. Magically, we lined up for the most part right in our calibration limit. And we'll dive into some data in a little more fidelity here, but we did include normal things from a 1600 series EPA method, like a methoblank and an LCS and an LCS dupe, as well as the time equals 0 for the gloves in question. And we've included things like the backboard and the street surface as well. So you can definitely see the largest contribution here was that basketball after half an hour of play. Beforehand, it was non-detect, and afterwards, and I did just wipe one swath of there are eight patches on a basketball, and so that's about an eighth of the basketball. But it readily picked up 6 ppd quinone from the street, and then subsequently seemingly deposit that onto the gloves of the players. So we'll zoom in a little more to the players' hands themselves. The gloves, nice and clean, that's great. We use those same gloves here at the laboratory. And then we had 4 different players with pretty similar recovery or pretty similar detections here for 6 ppd quinone, but in all cases, we were detecting 6 ppd quinone on the gloves. I should note that player B was more aggressive than the other players and was a bit of a ball hog, and you can see that reflected here in these data. And this is only after half an hour of play, but sizable detections that we found here. The basketball, we'll zoom in a little bit on the basketball. Again, that was 1/8 of the basketball that was wiped, but it was just a nice section that I could get one wiped sample to cover that amount. So that was 30 nanograms on that section of basketball, but it readily picked this up from the street. In fact, it was higher than the street because it's just concentrating that. We think it's concentrating that 6 ppd quinone as you're dribbling the basketball, as one does. The backboard, please pay attention to the y-axis here. The backboard really didn't change much. It had some background on it beforehand, and even after half an hour of play, it went from 1.4 to 1.5. So it stayed about the same. So the 6 ppdq was not seemingly getting concentrated onto the polycarbonate backboard. This is a slide on our recovery, our internal standard, our ES recovery. Great recovery across the board. Love to see something with pretty much high 70s to 90% recovery. We knew that our test was performing well with this matrix. Chromatography examples. I'm a chromatographer, and so I like to say, what does it actually look like on the instrument? You can see that our continuing cal, our LCS, and our glove samples all looked about the same, which is what we strive for. We're able to give precise quantitation when we have nice chromatography, and I think this is pretty nice chromatography. One thing I want to touch on, even though that we can't ethically report the parent compound as a precise number, we do offer a presence absence in the background. And so in all cases where we found 6 ppd quinone, we are seeing what you're looking at here is the parent compound 6 ppd. We can get 2 ions, 2 MRMs for that compound, and we saw a reservoir. So this 6 ppd is going to continue to react with ground level ozone and potentially change that 6 ppd quinone level. So again, 6 ppd, the parent compound, is a reservoir for 6 ppd quinone. And I think that part is really interesting. So conclusions, next steps. Yes, the spoiler, it does seem like playing street basketball is a potential exposure pathway for a 6 ppd quinone. I would imagine we're going to be talking about biomonitoring more and more in the future. But we didn't see the backboard go up too much, which I thought was pretty surprising. Maybe it's because it's polycarbonate. And again, this mini study was only after 4 days, 4 dry days. And we did have 1/3 of an inch, about 7 to 8 millimeters of rain on that 4 days previous to this experiment. So it was it was in 4 days. I thought we actually got some pretty sizable detections. And just like your mom said, you should wash your hands after you come back inside because you never know what's on them. And with that, I think we're all done.
Right. Andrew, thank you so much. And our last presenter for the Lightning Talks round today is Rachel Scholes from the University of British Columbia.
Thanks, Tanya, and thanks everyone for making it through all the lightning to the final lightning talk today. So I'm Rachel Scholes. I'm an assistant professor at UBC in Vancouver, and I'm going to speak about a couple of case studies that we've done in my research group looking at how well 6-PBDQ is retained or treated in green infrastructure systems. I'm going to focus on two different types of green infrastructure systems today. We've been doing quite a bit of work on green infrastructure, but today I'll cover essentially two case studies, one on each of these types of systems. One is stormwater retention ponds, which are quite commonly used in urban areas to slow down stormwater flows, and then bioretention systems or bioinfiltration systems in which water filters through soil. So the first case study is on a retention pond that's located in Surrey, BC, just south of Vancouver. This is called the Quibble Pond. It receives runoff from an adjacent busy roadway into an inlet structure. You can see here the flow path of the pond shown in the red arrow. Essentially, water flows in through an inlet structure. It goes around essentially a 180-degree bend around a berm and then exits again near that inlet. And so in this system, we were able to collect samples throughout the flow path of the water and analyze what was happening with both solids to see if they were settling out, as well as 6-butadiene. Because we know that 6-butadiene is a somewhat hydrophobic compound, part of what we were trying to understand about its fate in retention ponds is whether it gets removed with particles as they settle out of the water column, or if it passes through these types of pond systems. And so to try to understand if there really is a benefit to these ponds or whether the sediments are really just a reservoir of contaminants like 6-PBDQ. So to test this, we show data from two different storm events that we sampled before, during, and after. And the first was quite a heavy rain event. And in this rain event, we actually had so much rain that berm in the center of the pond got overtopped by water flow. And you can really see this in the data that we have for the 6-PBDQuinone concentration. So here I'm showing concentrations of 6-PBDQ collected at the inlet and outlet of the retention pond. And overlaid from the top is the rainfall intensity, so coming down in blue. And you can see that shortly after the precipitation started, we quickly get an increase in 6-PBDQ concentrations entering the system, entering the pond. And you can also see that outlet concentrations closely track the inlet concentrations throughout the rain event. So during this rather intense rainfall, we were not seeing any retention of 6-PBDQ. You can also see that even particles were not being removed from the water column in that first initial flush of the pond, and that's during the period where we think there was a lot of short-circuiting of the pond system, so actually the water wasn't even making it down around that bend. But later in the event, we were seeing particle removal and still not 6-PBDQ removal. So during the heavy rain, most of it just passed right through the pond. Cool. Sorry, also dealing with slide delays. And then we sampled during a second sort of more moderate or lighter rain event. You can see this is sort of characteristic of a lot of rain in Vancouver or Seattle, of sort of on and off, not very high intensity. And in this rain event, we actually saw some retention of 6-PBDQ or some decrease in concentrations moving from the inlet to the outlet of the retention pond. We're not seeing like high removal, right? We're not seeing 90% removal or anything like that, but there is some decrease that coincides with removal of particles from the system. And so during this rain event, we had a longer hydraulic retention time. The water spent longer in the pond, and The removal was by no means consistent, but we observed some. Okay, so that's our story, our quick case study on retention ponds. We've also done a fair amount of research on what happens to 6-PBD-quinone in bioretention systems. Our initial case study on a bioretention system was at a site in a residential area in Vancouver, and we actually conducted a spike test using water from a water truck, shown on the left here, spiking 6-PBDQ into this isolated bioretention system where we could collect water coming out from the underdrain. And in this study, I'm showing here just a figure showing the fate of where 6-PBDQ ended up in that bioretention system. We dosed in total 860 micrograms of 6-PBDQ. 76% of it, we believe, remained absorbed in the soil within the bioretention system. About 21% exfiltrated to the surrounding soil. This is an unlined bioretention system with surrounding native soil. And then 2% of the mass made it into the underdrain, which would be connected to a storm sewer, for instance. So our conclusions from this were essentially that the bioretention system captured most of the 6-PBDQ. This is a system with a fairly high organic carbon content in the soil, a fraction of organic carbon about 9%. And this is consistent with the City of Vancouver's bioretention soil specs that suggests using 10 to 20% organic matter. We heard a little about this earlier, and the use of compost that is really important for 6-PBDQ retention. And this finding was also consistent with those findings that have been, to my understanding, with all the studies that have been conducted in Washington, finding that soil with compost or higher organic matter contents is effective for capturing 6-PBDQ. We have also, sorry, waiting on a slide to advance. We have also been looking at the effect of adding biochar into the bioretention media, and we've conducted laboratory column experiments to look at how long soil or soil amended with biochar can remain effective at capturing 6-PBDQ. So my student here, Ritu, who I like to give a shout out because she ran these columns for almost a year, to simulate 4 decades worth of Vancouver rainfall contaminated with 6-PBDQ, and found that over that entire period, we didn't have any detections of 6-PBD or 6-PBD-quinone in the effluent of those columns. So indicating that these systems potentially have the capacity to retain contaminants that are somewhat hydrophobic, like 6-PBD and 6-PBD-quinone, over long time periods. Which is encouraging to us that they won't serve as reservoirs that might re-release contaminants. We also have an ongoing field site where we're testing this under more realistic field aging conditions. So through a partnership with the City of Vancouver, they've installed side-by-side bioretention systems with their classical bioretention soil, and then next to a bioretention system that is amended with biochar at 3 weight %. And so we are able to take a look at what happens to these systems in the field and monitor over time to see how well they continue to perform for contaminant capture. So a few takeaways from these quick case studies. We looked at a retention pond. It provided some 6-PBDQ treatment during a smaller rain event, but not under heavy rain. We've found, both from this case study and other work, that bioretention systems that have sufficient organic carbon are quite effective at capturing 6-PBDQ, and that biochar might be able to further enhance the contaminant capture and prolong the lifetime of bioretention systems. Some of the data I didn't show is for more hydrophilic compounds that co-occur in road runoff that are not as effectively captured by conventional bioretention soil, but can be captured by biochar amended soil. And so I believe that is the end of my slide deck. I'll just say I'm happy to take any questions or have folks reach out if there's anything in addition you'd like to discuss. Thanks for the time.
Thank you, Rachel. Much appreciated. All right, so this concludes the live stream portion of the event today. We want to thank the presenters for sharing their work. We look forward to seeing everyone joining us on YouTube or TBW tomorrow for day 2. Zoom